Morning, everyone, and welcome back to Carla 2021 Latin America High Performance Computing Conference. On behalf of Carla 2021, I hope you have a very nice day, and now we can start the activities of this day. We start with our first panel of the day on the subject of Africa and Latin American HPC and AI cooperation. To introduce our speakers, now I give the floor to Bianca Amaro, your first moderator of the day. Bianca.
Thank you. It's great to be here with you. And I will ask to Philip to introduce our panelists for today.
Okay. Thank you, Bianca. It will be a pleasure to present very fast our panelists. I will open the web page with our panelists. So the first one is, let me share the screen. That is more easy. Okay, so let's share. So the first one is Happy. No, Happy is from the National Integrated Cyber Infrastructure Initiative. I need to see all the screen. I have a little problem with the screen. Let me see. Where is my screen? Yeah. Oh. And yes. Okay. It's better now. I was not seeing that. Happy is the center manager for the South African Superstructure System in NICA since 2019. He's responsible for the coordination of the system so that it meets the demands of the South African National System of Innovation in support of the Department of Science and Innovation. Is involved the three main entities of the CI, Center for High Performance Computing, South Africa National Research Network, and Data Intensive Initiative of South Africa. I will go to the next speaker because we don't have time to continue to read all the the next member of our panel is Matthew Mutumbuka. He is from Ubuntu Net Alliance. Dr. Mutumbuka has served as the president of Malawi Institute of Engineers for 2 years and as chairperson for the Connected Network, an association of IT professionals in Europe. He was executive director of the Malawian Initiative for National Development and president of the Oxford University Africa Society. He currently sits on board of several companies and organizations in Malawi, including NBS Bank, Nikon Technology, and Responsive Safari. Previously, he served as vice chairperson for the Council for Zuzu University, among other university governance roles. Let's go to the next speaker. Luis Eliezer Cadenas is executive director for the Clara, born in Venezuela, and with a vast experience in the academic network and the Latin American ICT scene. Luis Eliezer Cadenas started to work as executive director of Red Clara on August 2017. He is a computer engineer with postgraduate studying in economics, telematics, networking, and computer science, with almost 30 years of experience in information technology and telecommunication field, both in the private and public domains. In his professional career, the Venezuelan Luis Eliezer Cadena has sought to be an agent of change, growth, and developments of people and organizations through information and communication technology. He designed his role as co-founder, president, as member of the board director of the National Academic Network of Venezuela, Relación, in which he had a center participation between 1996 and 2000. Was fundamental. As president of Producción, Cadena sought to align the organization infrastructure and resources to the needs to the university and research and academic center of his country, achieving the development of his first national physical network, connecting 17 public universities, increasing the availability of bandwidth for the scientific and academic community. Okay, let's go to the next one. Myself, Philippe Navot. I'm professor of the Informatics Institute from the University of Rio Grande do Sul, Brazil, since 1971, graduated in electronics engineer, with a master in applied physics and a PhD in computer science at the INPG, Grenoble, France, professor of graduate and undergraduate course of computer architecture, high performance computing, leader of the group Parallel and Distributed Processing Group, with project financed by Brazilian government agencies and also international cooperation with project of Europe, with group, working with group from Spain, France, Germany, and USA. I also participated in project with Microsoft, Intel, HP, Dell, Altus, and others. Has oriented over 100 master and PhD students and published more than 400 papers, etc., etc. And our moderator, Bianca Amaro. Nice, Bianca. Dr. Amaro holds a PhD in applied linguistics from Pompeu Fabra University in Spain, acts in the following subjects: scientific communication, corporate, open access to scientific information, and open science, coordinator of the Brazilian Open Science Program at the Brazilian Institute of Science and Technology Information, IBIC, winner of the International Electronic Publishing Trust for Development Award, 2015, member of the Executive Board of the Confederation of Open Access Repositories, president of the Federated Network of Institutional Repositories of Scientific Publication. LA reference. That's it. Bianca, it's your. I think it's a good idea. I speak a lot to choice maybe one of our partners from Africa to start.
Well, I don't know who invite first, but I'd like to, first of all, I'd like to say thank you for the invitation to moderate this event, this panel, that it's very, very important. I will invite, at first, I don't know, I will invite Luis Cardenas to the floor, to be the first one. And I would like to say to the audience that you can put your questions in the Q&A, and then we will do it to our panelists, okay? And thank you for all the audience, and let's start. Luis, the floor is yours.
Thank you, Bianca, and thank you everybody for this this kind invitation to participate in this very relevant panel for us. I would like to begin with a quick introduction of the relevance we find in the cooperation with Africa. In particular, as you have seen, maybe in other presentations during this event, in Red Clara, we have been able to build an infrastructure that is connecting right now all the continent, and is connected also to the rest of the world through the connections and connectivity that we have been developing. The most recent is the subsea cable that we inaugurated a few months ago, connecting Latin America with Europe. Is the Vela cable, which is offering us a lot of capacity to integrate the collaboration, the scientific, academic, and technological collaboration between Europe and Latin America. And we have also a connection, a similar connection with Africa. Since the past year, we signed together with Matthew, who is the CEO of UbuntuNet Alliance in Africa. We signed a cooperation agreement in order to explore and increase the collaboration between Africa and Latin America. And I would like to mention several aspects of this collaboration. In the past, we have worked together with African networks in projects that has been funded by the European Commission, like MAGIC or Tandem. Those projects have been were several years ago, but now we have this new connection with the cable of Angola cable that goes to Angola. And it's a big opportunity for us to increase the cooperation between the communities in Africa and Latin America. Because of that, the past year, when we celebrated the conference of Red Clara, we signed an agreement, Matthew representing UbuntuNet and myself representing Red Clara, to begin to begin to take advantage of this new connectivity that we inaugurated the past year. I think that it could be extended in many aspects, and one of them is HPC collaboration. HPC collaboration in Latin America has the history and the umbrella of ESCALAC, the supercomputing Latin American organization. And Africa also has several ways of organizing their HPC capabilities. But we are two communities in the same, more or less the same situation in terms of environment and resources and funds. And I think we, being in the global south, we need to partner in order to help those communities to get stronger and to grow in a way that can help us to create better opportunities for the region, for Latin America and for Africa. And I know that we have many things in common, and the reason of this panel was effectively to show those commonalities and to look for additional opportunities to collaborate and to cooperate in both sides, in both continents. We have already begun to do additional things. For example, La Referencia, Bianca is president of La Referencia. La Referencia is a Latin American repository, open repository, and is the Latin American, I don't know how to say that in English, Bianca. if the
Latin
collection
American network of
repositories.
Repositories.
Yeah, thank you very much for that. And we signed recently an agreement with Africa just to help also with the software and knowledge that we have been building for many years to develop the same things in Africa. And I think that this year, that is quite important because of the UNESCO future announcement, I hope, of the approval of the recommendation about open science. We are all in the same commitment to build the digital ecosystem for open science that we need in order to support the best use of public resources, funding science and finding solutions for all of us. No? So I wanted just to begin with this a small introduction to explain you the idea of this panel is to elaborate on those opportunities to have a conversation of how we can better engage our communities to grow the actions and activities that we have in Africa and in Latin America, and help each other to achieve the goals that we have as regions. So I will say that, Bianca.
Thank you, Luis. And I completely agree with you. I think that we have the two continents must work together. We have a similarity in our problems, and we have to adopt common solutions. And because of it, I'm so happy to be here and to know all the initiatives from Africa. Then I will pass the floor to Dr. Happy. Please, Dr. Happy, the floor is yours.
Okay, thank you very much, Bianca. And I would like to thank the organizers of this meeting. This is a very important topic for us to engage on. And I would like to thank Luis for the opening remarks, which I found that they are really in sync with what we are doing. So first of all, just to follow up on what he has commented on, the communication between Latin America and Africa, I think it's improving much better because of the connectivity that is being improved in the continent. I can just say from our side that we are also investing heavily on international connectivity. We use what we call the West Africa cable, that we are currently expanding our connectivity in that area. It is mainly driven with the fact that we are looking at hosting the square kilometer array that we are in a process now for the astronomy project, that we are already receiving some data from the initial telescopes. And with this, we have got some of the Latin American countries that participate in that experiment. So we already start seeing data being shipped through this. But with this connection also, we have got investment on the CCOM, which also we use it as our redundant connectivity, but also link up the rest of the East of Africa. So this makes it easy for us now to be able to collaborate. And the other point that you have, Luis, that you have mentioned is the investment in the science experiments and mainly digital experiments. And here in high performance computing. In about 10 years ago, it was only high performance computing in South Africa. But over the time, we have built capacity in most of the African continent now. There's computing capabilities there. And there are very important science and engineering subject matter that needs to be addressed. First, like astronomy, but you have correctly indicated some of the things which are common here, looking at things like climate change, climate modeling, which is an interest of our countries. I think here, and maybe Philippe will touch on it, already there is initiative that South Africa, Brazil, and other countries are already working on, because they have identified common areas of interest in looking at digital Earth. I think these are very tangible things that will also push us to work together. And also on other aspects that I'm looking at in terms of health, we are looking now, especially now with the COVID-19 pandemic, we realize that the world has to work together. Already there is communication with some of the Latin American countries in working in these subjects. So with this efficient connectivity and with this projects that I have highlighted, including space science, which is one of the areas of interest amongst our continents. I see a lot of synergies that we can be able to leverage these investments and have cooperation in our countries. So I very much look forward for the discussion in this topic. And if at some point it's necessary, Bianca, I can be able to share more about what is happening in Africa and show some pictures. Thank you very much. I'll leave for the other colleagues to comment.
Thank you a lot, Dr. Happy. Well, let's pass the floor to the next panelists. That is Dr. Matthew. Dr. Matthew, the floor is yours.
Thank you very much, Bianca. Yes, so as Louise mentioned, we have a partnership with the Red Clara, the MOU that we signed, and we're doing things together. And then we look forward to also building on that MOU to do things together in terms of the HPC. There are things happening in Africa here in the Ubuntu Alliance. My region covers Eastern and Southern Africa, 26 countries. In South Africa, there's a lot of HPC happening, Zambia, Kenya, and then a little bit in some of the countries like Malawi, Somalia, and others. One of the things we see is that there is need for collaboration, as mentioned by Louise, in terms of sharing of the resources, for example. With HPC, you want computing resources which can pull from each other depending on where you have more need. So there's importance of connectivity. The good thing is, as Louise mentioned already, the Red Clara region is connected to the global connection, just like we are connected to the global connection. He's mentioned the cable that it goes via Angola, for example. So we already have the infrastructure that can enable collaboration through HPC in terms of resources. The second thing is collaboration in terms of the research and analytics, doing things together across the continents, from Latin America and to Africa here through the MOU that we already have. And then the third collaboration is in terms of skills and competence. You know, we complement quite a lot. One of the reasons why Louise and I agreed when we met in February in America to work together in MOU was because historically, there's a lot of similarities between Latin America and Africa. The challenges that you meet there, most of them are the same challenges we meet here. And I heard from us that Louise has done a great job over the last couple of years to raise Red Clara to another level. So that's why I went to him and said, can we have an MOU so that I do not solve the same problems, you know, taking longer when actually maybe Louise has solved some of those problems. So I can easily replicate some of those things. And we can apply that same philosophy to HPC by working together, as mentioned by Happy as well, my colleague from Africa here. So I'm very excited to be part of this discussion, to look at how we can collaborate together, building on the MOU that we already have, and then cascading into HPC. Thank you.
Thank you, Dr. Matthew. It's wonderful to see all the things that we can collaborate our two regions. And it's fantastic. We have to get a union to go beyond beyond, to say something. And I must say thank you for you, and then we will discuss. We will try to discuss with all the panelists. And then I have the pleasure to give the floor to Dr. Philip. Please, Dr. Philip, the floor is yours.
Thank you, Bianca. Yeah, I will share my screen with some slides about SCALAC, that is a cooperation on HPC in Latin America. I hope you are seeing my slide. Yes? Yes. So what is SCALAC? SCALAC is an effort of members of institution, of university, of research group on HPC from Latin America and the Caribbean. I put some slides, very few slides. This is an idea when SCALAC begins. So SCALAC begins on 2013 in Colombia, with a meeting of people exactly in a conference like this one. And we discuss the possibility of join, as you can see, that what does SCALAC do? The idea is to promote the collaboration and partnership for high impact in the development of research and projects in Latin America, in HPC, but considering all the fields of the area of science that need HPC. So the idea is to share the advanced computing resource infrastructures, linked by Red Clara mainly, so with the help of Luis Cadenas, and it is idea, it's a non-profit continental needs of research and development. Currently, SCALAC is an entity legal with a legal inscription in Costa Rica. So this was doing in 2019. And we are developing, this conference is one of the things that we are a sponsor or working together. And we are also looking for initiative to, let me see the next slide to give an idea. So what is the idea of SCALAC is advancing computer support for people from all the Latin America, and to help the research and development, and propose collaborative interactions. So in this idea, there are a lot of initiatives that are doing. One of the infrastructure, as an example that can be shared, is the supercomputer that we had in Petropolis in Rio de Janeiro. This is the Santos Dumont supercomputer. It's a machine with currently 5 petaflops of power of processing. So the idea of this association is actually to help all the development in the Latin America between groups that need HPC. So the idea is to support this community and looking for infrastructure, looking for accessibility, to collaborate, to give a course, and so on. So as an example of initiative, with the help of other institutions, as you can see, like RECAPS is a project, Ibero-American project, RISC is another. With Grid 5000, this is a project of machines in France, with Exceed from US, and with Compute from Canada. So this kind of share of machines can help us. As an example, with the help of finance of this project, that's in Ibero from Spain and Latin America. We share infrastructure from our data centers. So here is the sharing from machines from Mexico, from Colombia, from Brazil, and also from Spain. And so you can see we help especially science researchers from needs from all the countries from Venezuela, from Chile, from other, the needs processing time. And so you can see some of the calls that we help with, as you see here in 2019, more than 2,600 hours, or 2,600,000 hours of processing CPUs, and from graphic processor units, something like 7 million of hours of processing. So this is the idea. The idea is to help with infrastructure, with course, with conference, with workshops to improve the cooperation in Latin America. I think that this example of SCALAC is something that we can develop together with our friends from Africa, so we can also develop a cooperation between our groups, within our university, our research groups, to develop better cooperation and better offering all the groups, power of processing, and also acknowledgement that is very important. So some of the actions of SCALAC is the conference Carla, like this one, that workshops, bird of feather. This is interesting. In supercomputing conference in USA, all the last years we had bird of feathers, so we had a moment to present and discuss the cooperation in America. So we are calling this America's collaboration. And in the next supercomputing that will be at St. Louis in the USA, I think it will be virtual, the conference. And we had the BAFLA to present the results of this cooperation. So I will end with the last slides with some links with more information, and a photo with the last conference, presential conference in Puerto Rico, the Carla conference in 2019 with peoples and students in this conference. So thank you.
Thank you, Philip. Thank you a lot. I have some questions to all the panelists, and let me start. The first one is, how could we develop collaborations in the training of human resources, in the point of view of each one here?
If you let me, Bianca, I can begin suggesting some potential actions. I think we need to have a coordination mechanism between us, and after I'm going to ask also to our friends in Africa if they have an organization similar to SCALAC, because as you know, in Latin America we have several organizations that are working in different aspects of supporting science through technologies. This includes La Referencia, SCALAC, Red Clara with the connectivity. And what I think is that we can agree in a common agenda and probably work together and have a point of contact, a frequently point of contact between both regions to plan different projects, including training resources or educating our people in terms of using the capabilities that we have. There are, I think, a long tradition of cooperation between Africa and Europe, and also between Latin America and Europe. Probably we can work the three regions together to build a more stronger approach to the needs of this community. Maybe having a point of contact, maybe an annual meeting, or maybe a biannual, or maybe with more frequency, to meet with each of our partners in Africa. In the case of Africa, there are several research and education networks. Maybe we can agree in having a common meeting and explore the options to complement the things we are doing. I think, and I am sure that ESCALAC also have all the interest and all the goodwill in order to be able to build something better, and to learn from each other, no? With the different experiences that each of one have. I imagine a lot of lines of research and activities that we can foster. For example, in climate change is something that is quite relevant for the world. How we can support research in climate change with the addition of our capacities, and aligning our efforts in order to prioritize different things that could be really relevant for both regions. So I think we need to create this space. We have several of these meetings, but we have not anyone specific with Africa. I met and I meet with Matthew in the CEO Forum, which is a global organization that connects all the CEOs of research networks in the world, or a part of them. We have another meeting that we have been doing now for 3 or 4 years, which is the America Summit of Academic Networks, where we meet with Internet 2, and we meet also with Canary in Canada. We can do the same in the case of Africa and Latin America. We can have a meeting, a regional meeting of both continents, and to use this meeting to commit goals, to make alliances, to plan with projects, and to share experiences. Is something that could be very, very helpful and very interesting for us, at least.
And our African friends, do you have any other idea?
Yeah, I just wanted to add to say, in terms of the training, I think that it happens, but very limited. If you start at undergraduate, the training in terms of collaboration is through the project work, teamwork, which is collaboration within, say, the same program, the same university. So it's localized, not across countries, across continents. I see a trend where there's a little bit of change. For example, my former University of Malawi, I've seen there's partnership with some American universities where undergrad students in America are coming to Malawi and working together on drones and systems, and some Malawian students also going to America. So there's a limited of that. At postgraduate level, there will be, again, very limited collaboration. But what I see is that most universities focus on training for collaboration for researchers and academics. So at that level, that happens. But then specifically to high performance computing, I wanted to share, let me just share my screen for 1 minute. I think that in Africa, there is something that is interesting where there is a little bit of collaboration and sharing. I hope you can see, Bianca, my screen.
Yes, it's okay.
Yes.
Yes.
Yeah. So, as you can see here, we have the Center for High Performance Computing in Cape Town, South Africa, which provides a lot of support in terms of setting up high performance computing. And also, our researchers within Africa can register as principal investigators, depending on the themes for their access. And they provide even training, capacity building, as well as to clusters in Botswana, Malawi, Namibia, Ghana, Mozambique, Mauritius, and many other countries. And now they help also build their own supercomputing machines, and we have a lot of very high performance systems across. So I think this is a good start, but as Louise has mentioned, there's far more that we can do, especially between us here in Africa and Latin America. Thank you very much.
Yeah, maybe I can just add on what Matthew and Luis have just indicated. Those are a lot of opportunities for us to build capacity. The initiative that Matthew just highlighted now, this is an initiative that we started to build capacity in the rest of Africa. Initially, high performance computing was just in South Africa. But our view was that for sustainable high performance computing in a continent, we will start off with helping people to be able to build the cluster from scratch. Because if people can be able to understand the technology, and then from there understand how they can be able to manage the systems themselves, then they can go into the utilization. So we have got a full package that we have developed and worked together with a lot of these countries on that. So coming with the pandemic, because we could not travel anymore, we had to quickly look at how do we take all this information and package it and put it into online course. So we already have got a team that is supporting the researchers in this. And this course now is online. And we have seen that we have a lot of countries that are taking this course at their individual pace. So it's something that we can be able to collaborate on. But the other thing is in the meetings that you have mentioned, like supercomputing, we also are on above there at SC that looks at training and the global training. I think I met Carlos in one of that those meetings. It could have been in Denver. So it's another opportunity where we also have partnership with the colleagues in Exceed because we do a lot of also programs with them. And Luis, you have correctly indicated, also in Europe, there are a number of other projects that we work together with them. One good example is a triangle where we're looking at the development of capacity of HPC in Mozambique, and we're working together with Portugal in there. So this was a three-way collaboration. And we had also Texas Advanced Computing in the US working together there. So I think it gives us a lot of opportunity to have training programs there. One program that we have also is on the Student Cluster Challenge, where we bring in young students into high performance computing. And I've seen Mexico being part of the initiative. We met in Germany with the teams from Mexico, and I think other Latin American countries participate in that. I see that an opportunity that we can have Africa and Latin America competing in that. You would know that Asia has got their own competition there, where they bring in the winners and go into international collaboration. So it's another initiative that we can think of, because a number of countries in Latin America already have got that. So yeah, I think we will be very happy to look at those initiatives. Lastly, I would like to say we have got an annual conference on high performance computing. It takes place every December. In this, it is in the same style as supercomputing conference or international supercomputing. Normally, our community. When it is physical meeting, we get about 700 delegates. The past 2 years, we ran it virtual because of the pandemic. This year also is still going to be virtual. We're hoping next year we can have a physical meeting. And we would like to be taking you to the most exotic place in South Africa, right in the Kruger National Park.
Oh, yeah.
Where we host the, yeah, Philip, I take you with
With the lions.
yes, of course. High performance computing with the lions. It will be the second time we hosted there. So it's an initiative we would like to get. And I think in our last physical meeting, we had representation from Brazil in that meeting. So it will be good to extend and have Latin America also to participate in there. We have got training programs there. We have got science presentations, and we have got also technology discussions. We get support from most of the OEMs. I see some of them, they are the sponsor of this meeting, like your Alta, HPE, and the like. They also support this meeting. So we share about the successes in technology, the use of high performance computing, but at the core of it is also training. So we very much welcome the initiative. Thank you for the question, Bianca.
Fantastic, Dr. Happy. And you, Philip, Dr. Philip, do you have any other idea, any other fantastic idea?
Oh, there is a lot of fantastic ideas, yes. Now, I understand that this panel is one of the first initiatives that very important to the cooperation, the collaboration between our countries from Africa and from America. No, when I say America, I'm saying also the Latin America. No, it's important to remember something. Millions of years in the past, Africa and South Africa was connected. It was just one. Now we can see exactly now in the board of Africa the same shape in the north of Brazil. It's exactly the same. No? So I understand that this panel and the other initiatives that we had in the last years, it's very important, because I understand that we can have ideas from one country to other country to exchange experience, and this is very important to help the development of our countries. We need that. We need that. And so we looked at we had some groups that had a good acknowledgement, a good infrastructure, and we need to share this with the other that don't have the same opportunities. No, but with this work of sharing information, sharing knowledge, sharing infrastructure, no, we can help the development of our countries and the development of our society. You know? We had some works with South Africa in Brazil, because we participate in the BRICS. You know? BRICS is the project of Brazil, Russia, India, China, and South Africa. You know? So we had some project. Currently, we are preparing a project on areas on health, on climate. No, so it is a cooperation, but it's a cooperation with together China and Russia. What we think that we can maybe work with our governments, our institution to have something between Africa and Latin America. Why we don't have a call to project together between our the two sides, developing some project on HPC and not just HPC, on data science, with a large word, currently data science in all the people are using data science, but it's a good name and we need to use. So why not have a big project, a call for project? But for that we need the help of the government, to put money to finance projects to developing this kind of stuff. I understand that is very, very important, and I understand that all the sides can have good ideas working together.
Fantastic, Dr. Philip. Thank you. Well, I have another question for all the panelists. At the same time that I invite all the audience, if you have any question, please put it in the Q&A of the Zoom, okay? Well, the question is, how could we develop collaborations in the training of, no. How can computing capabilities be integrated to form a common capacity between both regions?
Okay, maybe I should try this one, Bianca, first. And I think on this, I will refer to what we call the Global Open Science Cooperation. And the Global Open Science Cooperation is looking at bringing together their computing capabilities across the world. This is an initiative that we have all the continents participating in. I am the co-chair of this infrastructure committee. And what we are looking at there is to look at what sort of cloud infrastructure is available. Even though we still discuss to say it must not just focus on specific technology, rather we say distributed computing, because today it can be cloud, tomorrow it can be something else. I see in that initiative that the principles there is to look at, we're looking at the existing infrastructure. How can we let our countries work together in sharing the infrastructure? And this is something where we can see Latin America and Africa start looking at part of that testing, and with the view that later we contribute to the global open science platform. I think it was Luis or Philippe who introduced the concept also that we see with PRAISE. It happened in Europe, where this partnership in advanced computing is being successful. And one of the things that makes it a success is that we know that we don't have deep pockets in our individual countries. But the science require very deep pockets and various instruments for science to be successful. So it is only that desire that might help us to say, if there are various architectures in other countries, we get our countries to start share on those capabilities. The frameworks might be at the multilateral level, but also can start off at the bilateral level, where we have got bilaterals amongst our countries. I know that we had a couple of bilaterals that I attended to in Brazil, also Argentina and the like. So maybe we could look at those mechanisms for cooperation. Thank you very much.
I just wanted to add to what Happy said in terms of the four ways in which we can build that capability for sharing globally, and especially between the two regions. I think that the first one is in terms of resource pooling. So that there may be a time, and our time differences help us. Now here, most of Africa now is evening, yeah, and there it's morning. So it means in 2 hours' time, most of Africa will be sleeping and our computers will be idle. Then Louise can be using a lot of our African computing from now, because there's morning. You'll be using our resources for the next 8 hours as we sleep. When we wake up in the morning, we'll be using our computing and your computing power. So we'll have double capacity. You see, the time difference is our advantage for high performance computing here for Latin America and Africa. Very big, powerful, because the difference between you and me here now, for example, is 8 hours. And that's average difference with Africa. It'll be 4 to 10 hours. So that is an advantage, resource pooling. And then the second one is the research collaboration, which I think Louise talked a lot about it, and also Happy talked about it. And then number three, Happy talked about you need deep pockets. It's not cheap to buy HPC computing resources. But by coming together, we can have the efficiencies and the synergies. And I know already, Carla, you've been doing these things within your region. But now, collaborating across Africa and Latin America, we can even have better gains. And then the fourth one is in terms of capacity building, which Bianca was your first question we discussed already in the beginning. I thought I should share those. Thank you very much.
I would like to add something to Matthew's comment. I think that maybe once we begin with this collaboration, we will be able to plan together the needs that we are going to have, because of the same reason that Matthew has already mentioned. We can pool resources of both sides and dedicate them in the better way to support the initiatives and the research that is being doing in both continents. So maybe having a common, at least beginning to plan together what are the resources required, how we are using those resources, how we can connect them in an operative way that help us to duplicate maybe the capacity that we have already. Same thing is in the other areas where we are developing activities. For example, if we are providing courses, we should be sure that we are inviting our African partners, and also the idea of sharing it in an open format, that everyone that would like to access to the courses could have access to them. I think that joining forces, we will be able to duplicate the impact that we have in our communities.
Thank you, Dr. Luis. Dr. Philip, do you have any other idea?
Yes, I'm seeing that people are offering the questions. We had people offering access to equipments and offering to access cloud. So I think this panel gives some results now, because people are offering access to machines and offering to access cloud. But I think that something that we can discuss between us is that we are speaking about sharing infrastructure. No, it's very important. But we are in a changing of how work that is growing the use of cloud. So I think that this is important to discuss. Did we need to have a cloud between our countries? maybe it's an idea. Obviously, behind the cloud, you had data centers, no, to maintain this, but maybe we can share our machines in a cloud with the help of Red Clara, no, with the help of Luis Cadenas, no, and facilitate the access on all the groups, on all the little research groups, no? Because now with the access of the web, access to the cloud, all the people have access. If we had some kind of resource in the cloud, yeah, maybe it's a way to help the development, no, of little groups that don't need to have a big corporation or something like that, or structured corporation. They just access this cloud, a Latin American cloud, something like that, that can provide help for these little groups. It's a possibility, maybe it's not a good idea, I'm not sure about that, but it's an idea that maybe we can discuss in developing between Africa and between Latin America.
I would like to add something, Philip. I think this topic of cloud is quite relevant. And I would like to ask Matthew a little about the African Open Cloud Initiative. I don't know if you can share something with us, Matthew, because I think we need to look at this issue of how we are going to balance cloud resources with local computer capacity and those kind of things in an harmonic way, no? And in the correct balance in terms of what we need to use, how we need to acquire or to purchase those capacities, how we can join effort to, for example, get better deals when you are looking for services in the cloud. It's not the same thing to talk about Latin America or to talk about Latin America and Africa in terms of the process of purchasing those services. So I think there is also in this aspect of joining effort to purchase services and capacities, something that we can explore also a little more. But I would like just to ask Matthew a little about the initiative in Africa about this open science cloud.
Thank you very much. I think that Happy may add more because we have more of this happening in South Africa, but that we're in the initial stages of ended one of the conferences in Egypt 2 years ago before COVID. But most of the open science is largely concentrated in South Africa. And just like he mentioned about coming to Africa, the same with open science. A lot of it is happening in South Africa. Beyond South Africa, not much. But now we've set up as a Pan-African organization headquartered in South Africa, with effort now to expand to the rest of the region. Happy, do you want to add to this?
Yeah, yes, Matthew, I think you've got that on the spot at the moment. The African Open Cloud, it is still at a concept level, but the development of it is going to be based on using what already exists and start activities on there. My personal belief is that most of these initiatives will only succeed based on what already is on the ground. So it is important that we could start off with some of the projects which will become the beacon of this African Open Science Cloud when it happens. I know that the last time I checked, there was still going to be appointment of the director who will be looking after this, and also the funding mechanism from the various countries on that. So the existing infrastructure will be used as the starting infrastructure for this open cloud. So for an example, us in South Africa now, we already have got a cloud implementation that we're opening it up to a number of African countries. And all the time we report on how they have got access to our system. I think I can quickly just maybe just share with your permission here, Bianca, just
Sure.
to show on the, oh, how do I share? Oh, it's here, it's here, it's here.
Share screen.
Quickly, yes, just show with you on the screen here. And you can see that with our resources, we already report on how the resources are used. This mainly our South African academic institutions, public sector here, mainly from research councils, but we can see also the African partner countries using the resources. And of course, we also, on the private sector, we also report on that. So already there is that initiative to share the resources with the other African countries. And in our discussion, we have demonstrated the network is mature enough for this type of sharing of resources. So I would take that it will be the same if we want to extend this collaboration also with Latin America. Thank you very much. I have to stop sharing. Okay.
Thank you, Dr. Happy. Well, we have here in Q&A one point that Mr. Miguel Tiempos say that using containerized workloads, organizations can collaborate in organized fashion so that everyone is in sync with what is executed when and where. Anyone would like to say something about this point? Well,
Luis,
yeah.
say something, Luis. What do you think about?
Well, I think that we need to use all the options that we can use. No, I think that we need the real need is to find the right spot in terms of the balance between resources, investment, need of funding, and human capabilities. So I think that the most important thing is to have a common view of how we are going to develop that. I was going to just make a mention to the way we need to build these kind of things, and making an analogy to the open repositories, Bianca, that you know so well in Latin America. In Latin America, we have a strategy that is bottom up in terms of creating this way to integrate the publications, the open science publications that each institution has, because the institutions are very different in capacity, in size, in resources. So you need to plan thinking in small institutions, because the big institutions have already resolved their problem. The small institutions are the institutions that have not the option to do something similar to what I don't know, the Universidad de Rio de Janeiro can do. No, so I think this is the same approach we need to have in this other topic, in the case of Africa and Latin America, because when you see the actions in the global north, they are going in other way. They are going with a lot of funding, beginning with a lot of funding, and with a clear goal established and funded through public mechanism and also private mechanism. In our case, we have not this big or deep pocket, as you say, and we need to think out of the box in terms of looking how we can join efforts and use the best of our limited resources. So thinking in a bottom-up approach, I think is something that probably Africa is also in the same line, and we need to agree in protocols in a technical level, but also in common mechanism and procedures and processes to be able to integrate our needs and to build something that can be done with the resources that we have. It's very different to have an open science cloud in Africa than in other parts of the world. And also it's the same case in Latin America. We need to see how we can apply this concept in the right way to be using the resources in the best way that we can.
Yes, absolutely.
The same line of what Luis is saying, I understand that the problems that we had here in Latin America and the problem that they have in Africa are very similar, are not the same, but similar. And I think that Luis has pointed to an important aspect, and we need to develop a kind of approach to help the little and medium groups that, as he says, the big university, the big research group had access to some kind of solution and then don't have a lot of problems. But the medium groups and the little group need the opportunity. And if we can have something like a cloud, a science cloud, or other kind of sharing, but not sharing just infrastructure. You need to sharing training. You need to sharing knowledge to help the development of these groups. And I understand that is very important. This for our both side, Africa and Latin America.
Well,
I would like to add, sorry, Bianca. An evident proposal of our side is to see how we can begin collaborating, maybe with a memorandum of understanding between us, looking at some goals in this MOU, and maybe begin this capacity of collaboration between us, no? And begin to meet together frequently, talking about these topics and thinking how we can join forces and build something together. It's an invitation for our friends.
Good African idea.
Yes, I think that it's an excellent idea. And my last question, go to in the same direction. My last question, as we said before, there is a long tradition of cooperation between Africa and Latin America with Europe, and how these three continents could unite in a common goals.
If you like, I can mention something, and I let then the word to the other participants. I think that all the world has a common agenda in the SDGs, in the Sustainable Development Goals. And in particular, Europe has a focus in a couple of big orientations that are digitalizations and the green transition. I think that working together in aspects related to the green transition that are very close related to climate change could be a way to do that. We already are cooperating in this in some way. We are participating, for example, in Latin America, in America, in an organization called AmeriGeos, which is the organization that is managing all the monitoring systems and coordinating all the actions related to monitoring the Earth and the research related to the climate change impact and the things we can do in order to solve it. Same thing is in Africa with AfriGeos. There is also the same organization in Europe, and all of them are together in the GEO, or the Global Earth Observation Organization, that is looking at this topic. Maybe working together in this topic in particular that could be of interest to all of us is something that we can do in order also to support a global challenge and a global goal as is the climate change impact and the green transition and all the movement that we need to foster in terms of using without damaging our dear Earth.
Anybody else?
Yeah, I want to add to what Luis said. You know, if we look Europe, we already talked about Latin America and Africa. So I just want to add the third leg with the Europe one. If you look, you find that Europe is at different stage than Africa and Latin America. And one way of looking at it is, I'll give two examples. One is the COVID experience, and the two is the differences in labor markets. So if you look at COVID, you will find that in general, Africa has been seen to be quite resilient. You know, nobody fully understands why, whether it's the climate, whether it's the genes or what. But to be honest, I am in Africa here. The scale at which COVID has impacted Africa is a tiny fraction of the impact in Europe. So obviously, there is a big need to understand the differences there. There is a big need for research to understand what lessons can be drawn from Africa to help combat COVID. And the kind of parameters that will be involved cannot be dealt with the normal computing power. You would need obviously high performance computing. And then the second one is in terms of the labor intensive research, which becomes very expensive. In Africa, our day rates for even researchers are much, much smaller than Europe. So you could have the different levels of skills collaborating together, while Europe being far advanced, Latin America being in the middle, and Africa following behind that. And I think we can work out an economic model that helps us to collaborate together as we share the skills and the competences for us in the long term to be at the same level, while at the same time, in the present, we're being economically and financially very efficient in collaborating to produce the same kind of research results that we want. Thank you.
I would like to say something about what Luis and Matthews are saying. Is that I understand that working with Europe, it's very nice. I have a lot of projects with Europe, but also with US. But I understand that to be interesting for all the sides, it's important to work to a problem that all the sides had this same problem. So work together in a problem at the same level. No? So at the same level, I understand that we can develop a very interesting work. The problem is that when you had a problem that we had in Latin America, but in Europe, it's solved. It works, but it did not work very well. So we need problems that all the sides are at the same level, looking to solutions, looking to how find a way, research, and so at this moment we had a nice development and a nice interest between the parts to have a good working and a good cooperation and collaboration. For me, it is clear. A good collaboration is when we are working with at the same level with a good, a high respect between all the partners to develop something.
Fantastic. Our panel is fantastic. And
If I can just add,
please.
Bianca?
No,
Yeah,
see, yes, please.
Yes, yeah. No, I agree with the colleagues on what they have mentioned, and it will be good to look at what already exists and some of the problems that have been highlighted. I think they are possible. And also, I think what already exists between Africa and Europe is collaboration in astronomy. And I know some parts of Latin America also, like for an example with Chile, we have got the big astronomy project there. And this could be one of the areas that we can also look at. I would just also indicate that through that, there is already Africa and Europe collaboration under what we call IREP. So it will be easier to link up in that type of cooperation. And they might be willing to also look at how do we bring in Latin America. So this is one example. I think also in high performance computing, from our side, we have got an MOU with PRAISE on collaboration in a number of things. And we already have got some of the training programs that we're doing with PRAISE. So we're already collaborating in that. So I think it could be one of the areas also that we can look at under that collaboration to extend that so that we have got a three-way. So this is a good opportunity. And of course, I think what Philippe has indicated, sometimes in identifying the problems, it might take a long time. If we have to work on one common problem, it might be of interest to Latin America and Africa, but not a priority for Europe. So I think this is where we will have to make decisions that we continue just us and Latin America, and we leave Europe out. And there are areas where we will bring them together. So this type of collaboration also, it helps that it doesn't have to be all the time everybody agree. I think, Philippe, you also see this also under the BRICS countries. You can't get all the 5 countries agreeing on one problem. So those who are still procrastinating, we leave them and we continue. A good example is with the climate, the digital earth. It was only Brazil, South Africa, and Russia that went ahead. And when it was already at advanced stage, the other 2 countries only woke up and then they joined. So that's something that we can also use in our approach. Those who are on the bus, we let the bus to go, and the others catch up as the bus is on the road.
Very nice, very nice. I think, Bianca, that we need to end in 2-3 minutes, something like that.
Yes. And if I may, I'd like to ask to all the panelists some final words, something that you would like to highlight in our meeting. And I'd like to say thank you for the participation of all, the participation of audience and all the panelists. And my last words will be, we must work together, Latin America and Africa, is all that I can say. And I'd like to say thank you for all that have participated here. And who will be the first one? Go ahead.
Okay,
Dr. Happy, thank God.
Thank you, Bianca. This has been a very good panel, and thank you for you being such an excellent moderator, making us talk. And this was fantastic. I think what I really look at is something coming out of this, and maybe making a follow-up, but let's see some fruits of this. And thank you very much for everybody's participation. Thank you.
I can say thank you. I also thank you to all, thank you to the audience, thank you for the people that are organizing this panel. And I'm very happy to participate in the invitation. And I understand that what is very important is that this panel don't stop here. So we need to continue the discussion. We need to continue to work together to have something concrete between our countries, some kind of we can sign an agreement, something like that, to continue the cooperation between Africa and Latin America. And very happy to participate, and thank you very much all.
Yes, it's true. We have a lot of difficulties, but we are fantastic. And so we have to go together to be fantastic, to show the world that we are fantastic, two fantastic regions. Go ahead, the next, please.
Yeah, no, I just want to thank you, Bianca, for a very productive panel discussion that you facilitated and hosted. And I'd like to thank Philippe for very deep insights in what you do across and globally. And my brother, happy to know you now. When I'm in South, I'll give you a call. We can have a coffee and discuss more. And I'm sure we'll be engaging more to do this together. I'm happy that you complemented very well, on our African perspective together. And my brother Ruiz, thank you for inviting me. This is very enlarging, and let's build on our MOU to expand into HPC and other things together. Thank you very much, everybody.
Thank you, Matthew, and thank you, Bianca, and thank you to all the people participating in this panel. I subscribe the idea that we need to extend our collaboration, as Philippe mentioned. So we are going to begin to work here, not to end the work at this moment.
Exactly.
Yes, that's it. And so thank you for the audience. Thank you for the participation of our panelists, and see you in the next opportunity. Bye-bye. Thank you.
Bye-bye.
Bye-bye.
Bye. Bye-bye. Thank you all.
Bye-bye. Everybody, thank you. Bye.
Excellent. We thank you for your attention, and we invite you to stay connected. Having concluded this first panel and great discussion on this collaboration, we now continue with our first keynote talk, presented by Professor Catherine Jelic, entitled Machine Learning in Science, Applications, Algorithms, and Architectures. To introduce our next keynote speaker, please welcome Harold Castro.
Hello, everyone. I'm very happy to be here and have the honor to introduce Katie Jelic. Let me thank Katie for accepting being with us today. We have a very interesting talk, so I don't want to spend your time listening to me. We at Carla are really very honored of having Dr. Katie Jelic as keynote speaker today. It's a pleasure to introduce such a distinguished researcher to our community. Katie Jelic serves as the Robert S. Pepper Distinguished Professor of Electrical Engineering and Computer Science and a Lawrence Berkeley National Laboratories Senior Faculty Scientist. She joined Berkeley faculty in 1991 and is renowned for her parallel computing research. She's at her second year as an Associate Dean for Research in the Division of Computing, Data Science, and Society. As last news, she will be UC Berkeley's next Vice Chancellor for Research starting on January 1st. Her bio is impressive. So instead of having me here, let me give her the floor so we can all enjoy her talk. Dr. Jelic, welcome, and thanks for being part of Carla 2021.
Well, thank you very much for inviting me to speak. I'm very happy to be here today, and I'm going to talk a little bit about machine learning in science. Let me just make sure that everything is set up. Please let me know if there are any problems seeing the slides or in hearing me. So I'm going to talk, as Carla said, about applications, algorithms, and architectures. So machine learning in science, to start with sort of the applications question, what, why, how, and where are we going to be doing machine learning in science? So these are some images from some of the machine learning projects at Lawrence Berkeley National Laboratory, where I was a manager for about a decade, and recently, a couple of years ago, stepped down to return to campus. But I'm still involved in the lab, and there are a lot of areas in fundamental science, in the energy sciences, and in chemistry and biology, that, and as well as applied energy applications where machine learning is already being used in a number of scientific disciplines. So I think we can divide the types of applications of machine learning into roughly 3 categories. Of course, it's used a lot to simply to analyze data. That includes very fundamental science data, such as the data from the Large Hadron Collider in CERN. It's also used to accelerate the design and discovery of things like new materials. This is a picture of Christine Pearson, who leads the Materials Genome Project at Berkeley Lab, and looking at using computation and in particular machine learning to search through the space of possible materials. And it's also used to automate some of the scientific processes that we use. We think of this normally in terms of robotics, and that's what you see here, but there are other ways in which we're automating things like computational pipelines for doing massive high throughput simulations, as well as automating physical experiments. So this is a slide put together by Prabhat a number of years ago at looking at how machine learning is used, of course, on the internet for our most popular example, which is to find cats on the internet. And it's used for classifications, that is to answer the question, where is there a cat in this image? Localization, where is the cat in the image? Detection of other sorts of objects in the images, so not just cats, but dogs, and in this case, a rubber ducky. And then some segmentation, so you can identify exactly what the outline is of that particular cat. And he and another group of people use this also in climate, the same kinds of ideas in climate simulation data. So this is much more complicated data than 2-dimensional images of pixels. This is 3-dimensional data that comes from a scientific simulation of the climate. It's got many variables, it's got 3 dimensions, and it's looking for much more complex patterns. So the first question might be, they use this, by the way, for doing things like counting the number of hurricanes in a simulation. And you might think that, well, they're such an obvious event, why would you need to count them? But when you're running hundreds of years of simulation and you're doing it over and over again for different scenarios, the questions they're looking at are, how will the frequency and intensity of hurricanes change over with different assumptions about climate change? So the first question is, in the simulation, is there a hurricane? Where is the hurricane? Can you detect other things? This red rectangle is really looking at an atmospheric river, and then can you segment around them? And so they use these machine learning ideas with significant adaptations for this much more complicated case of scientific data. Now, one of the things we hear a lot about in machine learning today, and appropriately, is looking at fairness. This is something we worry about a lot in my role on campus as Associate Dean for Research in this new division of Computing, Data Science, and Society, where we're looking at the societal impacts of data science and computing. And so we worry a lot about fairness as it's applied to social applications of various kinds, but it turns out that notions of fairness also come up in the most fundamental of physics questions, such as separating signal from noise in the data from the Large Hadron Collider. And I won't read through these graphs here, but we're looking for trying to really look at the data that's coming from all of these particles and trying to detect which of them are noise and which of them are background. And in order to do that, we need to understand how the instrument is and what the bias is in the data that we're looking at. Natural language processing is also something well known in the AI community and an area in which machine learning has had a huge impact. It may not seem like it's quite as relevant to science, but in this project, also a kind of an offspin of the the materials project at Berkeley Lab. They're looking at analyzing scientific papers, and in particular the abstracts that appear in material science publications. And what they discovered is that you can sort of identify the structure of the periodic table from looking at the abstracts of these publications. And so this is a much deeper sort of analysis than simple textual analysis, but really trying to identify the key material science or chemical terminology, and then using that information that is gleaned from those abstracts to really try to understand something about the data. This next example is going to look at generative adversarial neural nets. And what we'll look at here is some, not just for images, and I'm sure you've seen fake images and things like that, but this is looking at videos, and we'll see if this is going to work. So this is of course, professional and experienced ballerina. These are two non-professional dancers and your graduate students. This is them appearing to dance by superimposing video and the learning a model based on the professional dancer and superimposing it on the two students. And so this is, in some sense, building data. And you may think, whoops, that this is not relevant to the sort of scientific questions that we're asking. If you looked carefully, you may have seen in that video that there were places where, for example, a hand disappeared. So there are a lot of imperfections in that. But this idea of generative adversarial neural nets is also being used to generate scientific data that people are using to analyze things like the universe. So this was used by a group looking at generating convergence maps of weak gravitational lensing. And they found that the generated maps were actually statistically indistinguishable from the ones that were produced by massive simulations. So it was a much less expensive way of generating these maps, and then they can use them to analyze the data. Now, this raises all kinds of questions that I will admit upfront about whether or not you can rely on these machine learning methods. Of course, people ask the same question about simulations. Can you rely on these simulations? But here we don't have the same kind of underlying understanding of, say, the equations or exactly the mathematical, the ways in which some of the mathematics are actually resulting in the power of the machine learning methods. And so, but I think it's a very interesting area, and one in which people are exploring a number of different techniques for accelerating either experiments or simulations by using these generative adversarial neural nets. Now, the next example, also taken from more of a design space similar to the materials project, although this is looking at drug design. and just the importance of the statistical machine learning techniques and the quality of those techniques to try to help search through a vast space of possible solutions when you're looking for, say, a particular drug to address COVID or something else. And this particular method is looking at ways of balancing between looking under the street lamp, if you will, or the spotlight, where you have training data and you've got results that are very close to the training data, where you have very high confidence in the learned properties of those other molecules that are very similar to the ones that you trained on, versus looking much further away where you have lower confidence. But if you never look further away, you will also never discover something that's maybe much more surprising. And so this statistical technique will help balance those two kind of trade-offs between looking nearby and looking further away. Now, in the materials area, and actually a number of other scientific disciplines, and one of the things that often does not come up in social or commercial applications is the importance of including physics into the machine learning model. Now, in some cases, you can train the machine learning model to learn physics, and that's really what's happening here in this work. It's looking at these molecular structures and the fact that a three-dimensional molecular structure at any rotation, so if you're looking at a two-dimensional image, which is really a projection of that 3D structure, you're going to see a very different two-dimensional image, but all of those rotations of that image, of that three-dimensional structure, are the same 3D structure. And here they're using these very simple sort of Tetris blocks, if you've ever played that game, very old computer game, but that there are some fundamental shapes here, at least, that can be made with only 4 blocks. And then you can take that's relatively small set of possible shapes, rotate them in all these different orientations, and teach the machine learning algorithm to maintain this property of rotational invariance. And so this is some of the ways in which scientific problems may be introduce new challenges that you don't necessarily see in other machine learning areas. Now, of course, the other very popular area for machine learning, or what is often just referred to as AI, is self-driving cars. So this has the advantages of automation behind it. And of course, there's a lot of things built into this in terms of image processing, but also control of the cars. And this can also be used in this idea of self-driving laboratories. So you may have heard of lab in the cloud, the idea of putting, say, biology laboratories in some shared large-scale facilities where they do massive high throughput experiments and do it much more efficiently because of, first of all, the ability to amortize the cost of having large robots that help automate the process, but also just the sort of infrastructure costs that can be shared across a much larger set of experiments. Now, one of the things that we look for at the labs is, and we run at the Department of Energy labs, are large-scale experimental devices such as the advanced light source and other light sources across the laboratory complex, the genome sequencers, the telescopes, the particle detectors, some of those shared, of course, even internationally, the microscopes, and also looking at embedded sensors in the environment. This is looking at sensors that are used to detect things like vibrations, such as earthquakes that are embedded, and as well as applications looking at problems such as energy use or health applications that are on your handheld devices and other sorts of sensors. So we have in science these representations of some of the same kinds of problems that people are looking at in areas such as self-driving cars. But here, the data sets are enormous. They're often, many of them, and when we don't get to the things like the personalized handheld devices, so cell phones and so on, we're looking at data that is fundamentally open and scientific and intended to be shared both across research groups, researchers within a group, but even internationally. And so it's important to be able to put those at a place such as a shared user facility where there's sufficient computation to be able to handle these sorts of data sets. And some of the light sources, for example, in the Department of Energy, started recognizing a few years ago that they could no longer really afford to put the computation that they needed for those light sources at the light sources. And so we built this model of really interconnecting the user facilities together so the data is streamed over a high-speed network, in our case ESNet, in order to reach the computational facilities. And then also to distribute that data all over the country or all over the world to researchers embedded throughout university systems everywhere. So just to sort of recap some of the cross-cutting themes that come up when we apply AI to or machine learning to science, there's the issue of the data being very complex, often three-dimensional, often very sparse, and in some cases not very plentiful. So there are many cases where you have a very limited data set where you're trying to learn from that data that uses different sorts of machine learning techniques than, say, the deep learning techniques when you have very large available data sets on which to train data. So both supervised and unsupervised learning on very complex data. The fact that you often need to build in physics. So this image at the top is looking at an environmental sensor or taking remote sensing images and things like that. But what you want to do is to build a model from those images that is consistent with what we understand about how the atmosphere operates, for example. You often want in science, you want to be able to build mechanistic or physically realistic models that actually explain something. They don't just say, here's a black box and you can use it to make inferences from other data. You want to be able to explain what are the underlying equations that are learned from that model, and this idea of sort of interpretability of the models, which of course is a challenge for a lot of the deep learning methods. Fairness, as I mentioned, comes up even in science. Inverse design, so the problem of searching through a large space and using that to accelerate the design of things. Federated learning, where you really have a distributed network of sensors, for example, in the power grid or in the environmental example that I talked about. Transfer learning, where you may build machine learning for, say, a certain detector at the Large Hadron Collider. You then upgrade that. You'd like to be able to reuse what you've learned, the machine learning models, but adapt them to the new detectors. Uncertainty quantification is something that scientists care a lot about. It's a theme, of course, across machine learning, but especially in these scientific disciplines. In many cases, what's really important is to be able to quantify your uncertainties. Learning across the scales of the data set, and then being able to use it to control experiments. So I'm going to switch gears now from the applications and really talk a little bit about why are there advantages of machine learning in science, but and using the other disciplines to help explain this, and then go on to talk about some of the other questions. So this is a picture from the 2018 ACM Turing Award winners, which they won for, of course, for deep learning. And in Geoffrey Hinton's Turing Award acceptance speech, he said that I think a lot of the credit for deep learning really goes to the people who collected the big databases like Fei-Fei Li, and the people who made the computers go fast like Dave Patterson and others. Now, Dave, by the way, was sitting in the audience. I think there are many, many people who helped to make computers go fast. But Fei-Fei Li, of course, with her annotated and hand sort of curated data set of images has been really instrumental, as he says, in making the machine learning successful. And if you really look into the methods, although there's important work still going on, as I've tried to refer to now in some of the last examples of advances that we need in the algorithmic techniques for machine learning, it's also the case that some of these very basic techniques have been around, that have been successful, have been around for a long time. And what made them successful in 2018 and maybe the previous last decade or so has been the speed of the computers and the size of the data sets that we have to work with. And that is really, I think, something we need to think about as we look at scientific problems as well. So where can data, a large amount of data and a large amount of computing yield breakthroughs in science? So of course, we have some very large data sets and things like cosmology. This is the cosmic microwave background image. We also have to have very fast computers, which we also have in a lot of our scientific computing facilities, but then we need the scalable version of the algorithm. So this is a different issue than making the algorithms work well in terms of the kinds of answers they get out, for example, quantifying the uncertainties, making them converge quickly, and so on. This is looking at scalability of those algorithms. So in some sense, the parallel algorithms that are used to map them onto large-scale parallel machines. So I'm going to use a running example from my own research here, which is understanding the microbiome, because I think this is an example of where very large data sets and very large amounts of computing can lead to new insights and it's one that I'm familiar with. And I'll talk about both the kind of front-end data analysis problems, because before you get to a matrix that you can send into a machine learning algorithm, there's a lot of processing of the data that has to happen also at very large scales. And then I'll talk a little bit about some of the machine learning techniques. So first of all, this is a very large data set. This is looking at the microbial data and the number of metagenomes. They're called metagenomes because with microbial data, many of the microbes, so think bacteria, fungus, and so on, are not isolated, that you don't just have that one bacteria by itself, say cultured in a laboratory. Instead, what happens is you go out and scoop up some soil and send that through a sequencer, and it may have hundreds or even thousands of different species in that sample of soil. And so that set of genomes is called a metagenome. And now the problem is to analyze that metagenome data, in which, by the way, the sequencer fragments the genome, and we have to put it back together again. And many of these species have never been seen before. So unlike, say, the human genome, we don't have a reference that we can align against. So some of the scientific questions that people have looked at that have very large data sets, one of them is what happens to microbes after a wildfire. It's something we've been very concerned about, the microbes that are emitted during a wildfire, but also how it's going to help or hinder the restoration of an area after a wildfire, something very near and dear to us in California because the large number of wildfires we've had here, but also other places, of course, around the world. How do microbes change across a 17-year period? So this is data, that 25 terabytes of data that's been taken from a lake in Minnesota called Lake Mendota. You're seeing here some algae blooms that have been forming. And of course, this is a big concern for anybody who likes to vacation and enjoy the lakes for swimming and fishing and other things, because sometimes these algae blooms can become toxic, and they have other sort of unpleasant side effects. But the microbes can also be a very healthy part of what makes the lake actually work in terms of the different species that they feed the smaller fish and so on. And you need to really understand how these microbial communities change. Now, what's it like to try to analyze this genome data? As I said, even for the human genome, and this is a little cartoon looking at some scientists trying to put together the 3 billion pieces, which refers to the 3 base pairs in the human genome, 3 billion base pairs, and trying to figure out how to put that together. As I said, the sequencers actually chop them into fragments. The current set of algorithms I'll talk about, well, I'll talk a little bit about some that deal with the kind of in production, mostly what are used at, say, the Joint Genome Institute, the short sequencers that spit out little fragments of DNA that are about 150 characters. And so those have to be put together in a puzzle. If you have the cover of the puzzle, that is, you know what the human genome is supposed to look like, roughly speaking, even though each human is a little bit different, you can put all the pieces together much more quickly. And I know this because we spend a lot of time over the holidays always putting together puzzles. It's very helpful to have that cover of what the puzzle is supposed to look like. For these metagenome cases, we have many puzzles, let's say 100 puzzles all dumped together, the pieces mixed together, and you also have the fact that sorry, I see there was a question here, and I'm happy to answer questions. I just didn't notice it in time, but and so you have them all dumped together, and you don't have the picture of the cover. So please just raise your hand if you'd like to ask a question. So here's kind of what a very high level picture of the scientific pipeline looks like for analyzing microbial data. We take a scoop of soil. We don't know what all the species are in it. The question mark here is referring to all the different species that are the genomes. We send it through the sequencer. We get out these little fragments called reads. We take them and we assemble them, and trying to turn them into a complete genome, we often get very large pieces of the genome, not necessarily the entire genome. These are called contigs. We then try to figure out which ones belong together and which ones are in the same species. And then we go through them and figure out what proteins are in those species. We can do that before or after figuring out what species they are, by the way, but looking at the contigs, we identify sequences, coding sequences that are going to code for proteins and convert them into proteins. Proteins now can be folded, and the understanding of the three-dimensional folding structure of them is very important for understanding the function of that protein. And you may have heard of AlphaFold or AlphaFold 0, which is a machine learning technique for folding these proteins now, which is maybe replacing the simulation techniques for a very expensive process of trying to fold proteins and figure out what their minimum energy state is, and then the process by which they get there, and then you can look at the function of those proteins and try to determine that. And we're looking at machine learning techniques that includes both the structural information, the 3D structure, as well as the sequence information from the protein. So this first graph, and this may be a little hard to interpret, but I'll try to explain it, is looking at this question of how big data and big iron can lead to new scientific insights. And this is actually not looking at the machine learning problem, but the earlier assembly problem. How do we take all these fragments of metagenomes and put them together into into contiguous sequences that we can use to identify genes and so on? And what you see here on this graph is on the x-axis, we've got some assembled data that we've put through it. And it turns out in this case, we've put in data that we know what the answer is supposed to be. We've actually taken pre-assembled species and chopped them up as if they had been put through the sequencer and mixed them all together digitally, and then put them through our assembly algorithms to try to see if you can reconstruct the species. The cumulative length of the answer is this 10 to the 8th on the y-axis, the dashed line there you see across the top. So you're trying to get a number of you're trying to get a contig length, a cumulative length that when you add it all together is equal to that. And what you see here is if you take a large number of samples, and this is, say, the multi-terabyte samples that I referred to before, and you co-assemble them as one big data set, the blue line here at the top, what you see is it asymptotes there to the answer. What happens when with the technique that was used before, or continues to be used in practice a lot, is they do what's called multi-assembly, where they take subsets of the data and they assemble it separately. And they do that often on a shared memory machine. That's the way most of the production assemblers work. And ours, the one that we're using, MetaHitmer, for the co-assembly is a distributed memory, large scale code. And in the multi-assembly case, what happens is that you can assemble these subsets, but they will end up giving you, in some sense, incorrect results that have duplicates in them that because you can't really tell the difference across these data sets. Now you can try to run a dedupe algorithm on the output of the assembly, and that's where you get the green line. But the point of this is that you can get better scientific results by looking at larger scale data sets and by using large scale computation. This is a little bit, a slide just talking a little bit about what I mentioned before in terms of looking at the three-dimensional structure of proteins as well as their sequence data, using a variation of graph neural nets with something called persistence to try to really recover information from about what the function is by looking at some known functions of known proteins, but looking at the relationships between them. So how do we use the large-scale computation? What are the parallel algorithms that arise in these? Well, let's talk first of all about the architectural space. Let's see, back in 2008, so more than 10 years ago, when I was heavily involved in DOE, we were looking at ways of putting together exascale machines. And there were sort of three possible configurations that we could think about. So we figured that we had petascale machines. We were going to, we were going to have to get at least 100 times faster performance out of them. And maybe there would be some increase in the size of the facility, but at most 10x in terms of the amount of power that we could imagine at the time. And we are seeing these exascale systems using 10 times more power than what we had we were using back in 2008. But the first approach was to say, well, let's just make the clock rates go faster. This, of course, is the favorite approach by the scientists, and one that we all knew even back in 2008 was not going to be possible. But it was sort of on the table just so that we could dismiss it. There was the idea of using accelerators and in particular graphics processing units, which were not so popular at the time, although they did exist in the Titan system at Oak Ridge in the US. And then there was the idea of using just smaller, more lightweight cores. And I know Satoshi Matsuoka talked yesterday, and I'm sure more about this sort of this swim lane, if you will, on the right. So we're looking at the competition between these different swim lanes. And today in the US, we don't have that third model represented. And of course, we don't really have the first model represented because we knew it wasn't possible. Instead, what we have are 3 systems coming out all with GPU-based accelerators. So Perlmutter, which is the system that's at NERSC at Lawrence Berkeley National Lab, and that's a pre-exascale system, but it is by HPE, which purchased Cray, of course, so that has the custom interconnect technology with AMD CPUs and NVIDIA GPUs. The other 2 at Oak Ridge and Argonne, and these are just the Office of Science systems and just the DOE systems. There are other things going on, of course, in other parts of the US. But as part of this DOE exascale program in the open science side, the second system here, Frontier, has AMD CPUs and AMD GPUs, and then the Aurora system will have Intel CPUs and Intel GPUs. So let me just say up front, this microbial analysis problem is one of the DOE exascale computing project applications. And we were sort of expecting when I started the project that our preferred architecture was going to be that third lane. It was going to be the many core architecture, not one of these GPU-based accelerators, because it didn't seem to have a lot of fine-grained data parallelism in it that we thought were so important for the GPUs. So when I talk more about the algorithms in a couple minutes, I'll say something about how we have discovered a lot of parallelism that maps onto the GPUs effectively in these applications. But just to look a little bit more about the architectural trends, of course, we're seeing enormous trends towards specialization. And I won't read through all the details here, but it just has a lot of example, including Google's tensor processing units. I think, and we're seeing this whole spectrum, including things like FPGAs, which have been around for a long time, but I think are becoming increasingly interesting as sort of the last architectural technique we have for making things go fast is to specialize it more for the computation rather than just having a generic processor that runs faster. And of course, we're seeing this across the world as well, and including the ARM extension that you heard about, as well as the Sunway chip in China and RISC-V extensions as well. And there's a whole wide set of companies looking at, of course, these specialized accelerators, in particular for AI machine learning applications, and in particular for deep learning applications, really. And that's my kind of cautionary tale and this is a picture of Google's TPU-based system, which of course you can't buy the TPUs, you can only use them on their cloud service, but, and these things have been optimized really for convolutional neural nets. Some of those startup companies are looking at other sorts of machine learning algorithms, including graph neural nets, but I think it's really important to think about when you have a very large community and a large investment going into a very narrow class of applications. To me, it's reminiscent of the high performance LinPack benchmark in HPC modeling and simulation. And of course, LU factorization and dense LU factorization is important computation in many scientific problems. But I think the community became overly focused on it because it was it still is in the top 500 benchmark, rather than all of the types of irregularity and adaptivity that we put in many of the scientific simulations today. I think HPL is actually a better benchmark for deep learning training than it is for many of the scientific simulation problems that we have. So the cautionary tale is just to be a little bit careful about getting too many people and too much money entirely focused on one algorithm or one class of algorithms. So my last comment really on the architecture is going to be about the difference between specialization and accelerators. And what I'm saying here is specialization, yes, accelerators, no. What do I mean by that? Well, I think that specialization is a really important technique, and even these GPUs, I will talk about how we are using them in a lot of these very irregular sorts of computations. But I think the idea of thinking of them as a sort of offload engine on the CPU, which means that that they're really not first-class entities in the HPC system, is really problematic. So, you know, we definitely need more cores, these very lightweight cores, more data parallelism, because data parallelism is the thing you're going to find the most massive amounts of in your applications, taking advantage of things like narrow data types and specialized architectures, something that we think is useful in the genomics space, more memory spaces, which is complicating the programming model. So it's something I'm not so thrilled with, but is probably here to stay. Putting the CPUs in control of everything. And that is something I think is a real problem, is that we've got all the computational power on the GPU, and yet the CPU is sort of in control of launching things on the GPU. And you can try to turn things on its head, but it's not really the natural model that comes from a CPU-GPU combination. And the last thing is really about the fact that for the most part, the CPUs are in charge of communication. And since, as we'll talk about, that's the most expensive thing we need to do on these systems, it's very important that we make it more efficient. This is a study that we did with some people at NERSC looking at the cost of doing communication on this was actually on the Summit system, which is one of the best cases, at least at the time, for an integrated CPU GPU. It has NVLink, the NVIDIA's own custom link in between the CPUs and GPUs on that system. So very high speed communication between them. And also the GPUs have a direct connection to the InfiniBand network through this NVLink or NVSHMEM sort of interface. This is the software layer on that. So it's a very good example of a tightly integrated CPU GPU system. And yet what we see here, and this is latency on the left, and the bandwidth or inverse bandwidth on the right. So in both cases, lower is better. And if you're on that system, on the Summit system, if you're just doing computation from the CPU, or sorry, communication from the CPU memory, you get this sort of under 2 microseconds of latency. If you're doing it from data that's sitting on the GPU, but you're doing it from the CPU, you get a little bit better, a little bit slower, sorry, a little bit worse performance, but not a little bit of overhead there. On the other hand, if the GPU tries to initiate the communication, which are mechanisms to do, and this is a combination of software and I think hardware issues, is that it still has to go through the CPU to synchronize, and that really creates quite a bit of overhead, and that affects both your bandwidth and your small message latency. These trends of the cost of communication have been going on for many years and are continuing. This is the trend in network latency, so it has improved. This is a log scale, so it's great to have something improve logarithmically over time. And memory latency is this other relatively flat line down here. And the point is that these other things, so network and memory bandwidth, the two blue lines are, the red line is the DRAM bandwidth, and the light blue is the network bandwidth. They have improved over time, but they're not nearly as quickly as the computational rate. So the gigaflop rate, which is the cost per flop, is in the dark blue here. And of course, the overall time to do something you can think of as the sum, or maybe the maximum if you want to overlap everything, of these different factors. So in order to think about how we're going to map these, our algorithms onto parallel machines, I'm going to kind of revert to something that we worked with many years ago in simulation, that Phil Colella at Berkeley Lab coined the dwarfs of scientific simulation. So it is particle methods, unstructured and structured meshes, dense and sparse linear algebra, spectral methods like FFTs, and Monte Carlo methods. And by the way, this last category tends to end up being sort of a catch-all for things that are massively parallel. I realize there are some complexities even in parallel Monte Carlo methods, but that's sort of how this last group of things, it doesn't affect quite as much how you think about the parallelization strategy itself. The national academies in the US put together a report on big data, and they knowing about this idea of the 7 dwarfs, called their 7 patterns or motifs the 7 giants of big data. And what's interesting to me is how many similarities there are between them. So there's something called generalized n-body problems that I'll talk about. There are some of these other algorithms. So unstructured meshes kind of correspond to graphs, although maybe somewhat different style of computation and algorithms on them. They compress linear algebra into a single one so that they could have a list of 7. In the work that we've done on genomics, we also wrote a paper on the 7 motifs. I would actually replace, I think it's very similar to what that report said, although I would replace optimization and integration with sorting and hashing, because there are lower level primitives that come up all over the place in these different problems, whereas things like optimization is still going to be built on kernels such as linear algebra and some of these basic statistics operations. So, and as I go through this, I'm going to try to compare and contrast 2 different ways of thinking about the algorithms and thinking about the programming. On the left-hand side, you have bulk synchronous algorithm, a very elegant model. You know, you compute, then you communicate. Your goal in doing in that bulk synchronous model for latency, to reduce the cost of latency, is to reduce the span, to use things like logarithmic algorithms rather than using order n algorithms in a parallel sense, or order p algorithms actually, for p being the number of processors. And then we want to reduce the data volume. And we'll do things like, we're going to try to tile the iteration space to try to come up with ways where you, and I'll say a little bit more about what that means, to reduce the total bandwidth. On the, and we can sort of abstract this in some algorithms with a sparse matrix abstraction, which is a very elegant way of describing the computations, even for fairly irregular problems, as you'll see. The other programming model, which is the one I've been using for most of my career and really advocating for, is an asynchronous model, or specifically a partition global address space model. But this is where we really focus on hiding the cost of communication. And the bandwidth optimization that we really have focused on here is for bisection bandwidth, which is going to come up in these applications. So all-to-all style communication problems. And the goal is to basically keep all the wires busy all the time, because that bisection bandwidth is often going to be your bottleneck. So you don't want to use a bulk synchronous model that has separate phases of communication and computation, because then you're wasting the wires, the most expensive thing in your machine, for all the time when you're doing computation. And this, as I said, comes up in these partition global address space models. So I'm not going to go through all 7 of these motifs, but I'm going to talk about 3 of them in just a little bit of detail, and 3 things that I think don't seem so obvious in terms of how they map onto parallel hardware and specifically onto GPUs. So the first one is building a hash table. And what we do in the genomic application, but I think comes up in a lot of data analytics applications, is making a hash table of something. In this case, we're making it of k-mers. So k-mers are fixed length substrings of the input data that we're looking for. And we use this all over in a number of different genomics applications, but we use it to try to put the pieces of the puzzle together in particular. So we're going to take all the k-mers and we're going to put them in a hash table, and we're going to count them. One of the reasons we count them is because if there are singletons in there, that probably means there were errors. By the way, I don't think I mentioned the sequencers also inject errors into the data. So we'll throw out all the singletons. There's only a single instance of that k-mer. But we're also going to use then the hash table to try to connect these k-mers back together and build what's called a De Bruijn graph. But so we want to take all this massive string data and turn it into these fixed length k-mers and count them. And this is a comparison of what it looks like to count them in the an MPI implementation that we originally started with, which is based on using MPI all-to-all V, so collective communication calls. We actually do use a Bloom filter because of the fact that we're going to be throwing out singletons. It has 2 phases. It has one phase to build a distributed Bloom filter, and then another phase to build the distributed hash table. But you end up having to actually communicate twice. And that makes it somewhat more expensive, but the Bloom filter is really helpful because it's a compact data structure. If you're not familiar with it, it's a statistical data structure that's very compact for just figuring out what the presence or absence of things. So you can use it so that you know whenever you've seen something a second time by looking at that Bloom filter. So that you've got a count of at least 2 for that particular k-mer. The partition global address space version is written in UPC++, and it is significantly faster, as you can see here. It's much less synchronous. There are no bulk synchronous phases. There are just these little buckets of k-mers that are being shipped out as soon as one of those buckets fills up. And if you do it without the Bloom filter, this bottom line just shows that it's even faster. And we're looking at techniques now of actually trying to do a single phase of computation with a more clever data structure. So that idea of reducing communication, of course, will come up over and over again, both at the application kind of algorithmic level and in the implementations of things like linear algebra routines. So in this K-mer counting, Nisra was a postdoc here at Berkeley Lab, and she built a version of K-mer counting that mapped onto GPUs, and that was running also on in an MPI version of the K-mer counting code, looking at that was built with MPI. And in this particular version, although I mentioned that the UP++ version was faster, this in this MPI code, there's actually very little time spent, just this little sliver of time spent in communication. The other time is spent parsing the strings into the K-mers and then counting them locally after they get to the remote processor. And so it's actually a very scalable code, which you might have also noticed from the previous slide. What happens when you GPU optimize this? And so this is now doing this counting on GPUs using the massive on-node parallelism from the GPUs. And basically, you may have heard that a GPU is a device that turns a compute-bound problem into communication-bound problem. And that's exactly what's happening here. That little red slice is turned into this big chunk that now dominates the overall runtime. Notice the y-axes are quite different here by 2 orders of magnitude. And working with John Owen's group at UC Davis, we've also been looking at, he's worked for many years on graph algorithms and things like that, and built a library called GunRock, which is the kind of comparison point we're using here for a graph algorithms, which also come up in these genomics problems. This is looking at comparing it to using more of a dynamic task scheduling approach, in which the GPU actually has a persistent kernel that just sits there on the GPU and is handling the tasks that are coming in and putting those tasks directly back onto the queue, as opposed to something discrete which goes back and forth where the CPU is really in charge again. And what you're seeing here is the normalized throughput. So you can think of this as the amount of concurrency at any given point in time as the breadth first search algorithm is operating. In the bulk synchronous case, this dark red line, what you see is that naturally a tree that sort of grows in breadth over time, kind of as you get to lower levels of it, is going to have much more parallelism later, but has very limited parallelism at the beginning. Whereas a dynamic tasking approach allows you to much more quickly get to high levels of concurrency and then end much more quickly. That does depend on the structure of the graph, and the right-hand graph is more of a mesh structured graph, but the dynamic sort of persistent kernel still does much better. Now, the second motif I'll talk about is generalized n-body. So what do I even mean by this? Well, let's start with the non-generalized, the simple n-body, and the dumbest possible n-body. So direct and all computations that come up all over the place in simulations, as well as data analysis problems. And the obvious way to parallelize this, although many people that have, say, molecular dynamics codes do something much more clever that I'll talk about on the right, but the obvious way to think about this, if you just sit down and say, well, I've got n particles, let's say 16 particles, I have 8 processors, I'm just going to give each processor 2 particles, and then I will cycle the particles, sort of a copy of the particles around to all the other processors, so that each processor is just responsible for updating the forces, if you're computing force interactions of the 2 particles that it owns. Seems like a perfectly reasonable parallel implementation. It turns out that not only does it have less parallelism in it, because you're of course limited to at most the number of processors equal to the number of particles, so 16 in this little picture, but it also has an unnecessarily high amount of communication. And so if you look at a better way to think about this is really replicating the particles on a subset of the processors. So in this case, making 4 replicas of the particles and then dividing them into, say, 2 groups that are going to be responsible for all of the interactions between those particles. And you're now only cycling around sort of one step in the way this is written. Of course, normally you'd have a much larger number of processors. So you do that with a smaller subset of thing. And each group is only responsible for a subset of the updates to say this first set of teal-covered particles, to teal-colored particles here. And what happens at the end then is you do a reduction. So you sort of have a broadcast at the beginning to get the different replicas. You run the algorithm there, but doing a subset of the computations in each subgroup, and then you do a reduction to get the final answer. And that's what's used in a number of these different very scalable molecular dynamics codes. The idea has been around a long time. What happens though when you've got a more sparse or irregular sort of interaction pattern? So the all-to-all, the generalized kind of n-body application that comes up in genome assembly is looking at another assembler that we're building that's based on long reads, where rather than chopping everything into k-mers, well, we'll still use the k-mers, but we're going to just try to figure out how to take two input strings and align them to each other. Now, alignment is a very expensive computation. It's order n squared in the length of the strings, at least in the worst case. There are lots of techniques that we'll use to make that run a little faster, but it still is very expensive in practice. So you don't want another n squared at the top of that, which is for all strings, match them against all strings and run an n squared algorithm on the string length. So that's just prohibitively expensive. So what you do is you say, well, if I want to align set A to set B, I'll put set A into a hash table. I'm going to take its k-mers and use those as keys, put them into a hash table. I'll then take set B, and for each one, I will compute its k-mers, look them up in the hash table, and only if there's a hit will I try to align those two strings together. You can use this when, in fact, in the way this picture is drawn, where set A and set B are the same, so you'll end up efficiently aligning all the strings to themselves, or for two different strings, which often comes up when you have, say, a database of genomes that you're aligning against. So we implemented this both in a bulk synchronous style in MPI and in an asynchronous style in which the communication is happening sort of all the time throughout the computation. And once again, you see an advantage in terms of the running time. Those are the two darker lines here, the lower one being the UPC++ asynchronous implementation. The lighter bars that are behind this are actually looking at the memory footprint for these different numbers of cores. And there seems to be a big advantage also in this. And you may have some intuition about why this happens, that the lower memory footprint for the asynchronous version is because you're communicating actually smaller chunks of data, and you're doing it more frequently. And that means you're not building up as much sort of temporary data that you're going to be, that you need to compute in the middle or communicate at a later point. Now, but you can also look at this irregular all-to-all problem as a sparse version of what I talked about earlier. So this is sort of the two-dimensional version of this computation, if you will, and turning it into a matrix. So imagine we have our hash table on the left here, which has our keys and then our strings in which those keys originally appeared. And then so we can think of that as a sparse matrix, which is a key by value sparse matrix. We can then take that and multiply it by its transpose, and what we get out, or actually multiply its transpose by it, we get out a string by string, or input string by input string matrix, which tells us what are all of the strings that have a common k-mer in there. And this then can be used for more of a two-dimensional representation, that is looking at the whole iteration space of read-read pairs, which is what each of the non-zeros that appears in that output matrix. And we parallelize over that matrix rather than parallelizing over the set of input strings. And this gives us much better scalability as well. Now, this is a bulk synchronous implementation. And what I'd like to do next is try to figure out if we can, because this implementation is in some sense much more elegant. You're not handling all this asynchronous synchrony directly. And you're actually implementing a much larger application, not just what I've shown here, in terms of these sparse matrix algorithms. Can we write at that level, but get the performance advantages of all the asynchrony under the covers? And the last thing I'll talk about here are graphs and sparse matrices, and kind of merge the two together a little bit, and just talk a little bit about the machine learning algorithms that happen on this data. So this is looking at graph neural networks, and this is just a picture of the computational kernel, and I won't read through it, but you're either familiar with this or not, but you're often going to multiply this very sparse matrix, very unstructured sparse matrix, by the way. So unlike a lot of sparse matrices that come up in simulations, by a tall, skinny, dense matrix. So this is a set of vectors, and you'll get a set of dense vectors out. And so this computation, this sparse dense matrix multiply, sometimes called SPMM, is the computational kernel inside of this machine learning algorithm. Now, how do we get matrix multiply to go fast? Well, to reduce its communication, and this was originally done in the dense setting by Jim Demmel and his group, the algorithm, though, had been around for a number of years, 3D matrix multiply, is again to think about the iteration space of the computation, not the matrices. So the natural way to divide up dense matrix multiply, and sparse for that matter as well, is to say I've got a C matrix, which I'm showing here in green. Let's just divide that into P chunks and say square root of P by square root of P chunks, and give each processor one of those chunks and have it be responsible for all the updates to that dense matrix, that little submatrix. Nice, easy way to write the code, but that turns out not the best way to do it from a communication standpoint either. Instead, what you want to do is think about the A matrix and the B matrix as well as the faces of this iteration space, where each point in this iteration space is a multiply add operation that will update some element of C using some element of A and B. And I can chop up this cube into, say, cube root of P by cube root of P by cube root of P chunks and still give us P chunks, which are larger in terms of the matrix size. And what I have to do when I'm done with each of those cubes is reduce or sum all of those the results of the little C matrices together to give you the final output. So that's sort of what the algorithm looks like. This is used in an MPI implementation and in a looking at these 2D and 3D algorithms for the case of sparse dense matrix multiply. Now, in this particular case, it turns out some of the 1.5D, what we call 1.5D algorithms, and I won't describe them here, but it's also ways of sort of replicating a certain amount of the data, but not quite as completely as I talked about in the previous slide, can give you some better performance, and you can replicate some number of times, which are the 1, 2, and 4 here that you see in the different graphs. So we explored a whole set of possible things. This is inside of the graph neural network framework called CAGNet. And we're also looking at an asynchronous implementation of this. This is work being done by Ben Brock as part of his work to build what's called the Berkeley Container Library. And this is looking also at optimizing that sparse dense matrix multiply. And I won't, there is a roofline model analysis that shows that it does very well. This tends to be a problem that is very very communication limited. So trying to figure out how to effectively use your network is absolutely critical to performance. And the lower lines here on the left are the Berkeley container ones. Those are based on this PGAS model. It's actually implemented an NV-SHMEM and this is with GPUs on the Summit system. So I'm just going to wrap up with kind of two statements as the take-home messages here. And the first one is that I think that there are tremendous opportunities in science for us to use machine learning techniques, including traditional deep learning or deep learning techniques, maybe non-traditional, but the deep learning techniques such as convolutional neural nets, but also extended to much more complex data sets that come up in science. And this example I'm pointing to is one that was identified a number of years ago at Fermilab, which is looking that the use of deep learning in looking at this particle detector data was like adding 4,000 extra tons of detectors because of the ability to extract signals from that data. And so I think we need to think also across science, where are there places that we can use machine learning to extract new science from old data sets, or build different types of scientific instruments that may not need to be quite as large or quite as expensive by taking advantage of the very powerful machine learning techniques. And finally, when we think about how do we implement these and take advantage of the massive iron that we work on with in high performance computing, that communication hurts. That communication is the most expensive thing we do, and that is whether it's for simulation, for data analytics, or for deep learning or other kinds of machine learning applications. And with that, I will stop, and I'm happy to take any questions.
Thank you very much, Dr. Jelly. That was a wonderful talk. There's plenty of avenues to discuss following your presentation. So I remember the audience, we can receive your questions through the question and answer tool in Zoom. And if anybody wants to ask, so please write your question. I will put it here on the floor. On the meantime, I would like to ask something that I was wondering while you were speaking, thinking on the talk we had yesterday about Fugaku, because you mentioned the architecture part on your talk, and yesterday Satoshi told us that one of the key issues of key success of their machine is that it excels on different applications. They say, okay, we are the best, we are number one on AI, on big data, on CFD, on any kind of application, and that was their goal. But if I understood well on your presentation, you advocate more for a specialization. And should we expect in the near future to have then different architecture responding to different kind of applications? Should we expect that the top 500 evolves towards something where we will have some some list for AI, some list for impact, what is your vision about this? Because I know this is the kind of this is one I am interested, but I know that others here are also interested on this evolution and what to expect in the near future.
Right. Well, it's a great question. And I think the first thing I'll say is I think what we're looking at today on the current HPC systems is sort of GPU style parallelism relative to more cores, more kind of independent cores with their own threads with wide SIMD units, right? So you still have some massive data or very large data parallelism inside of them. And I think I didn't appreciate this until we started mapping these irregular computations onto the GPUs, that really that part of the power of that is this kind of SPIMD model, right? A single program, multiple data model, where you start with a fixed number of threads and you keep all of those threads running all the time, and you try to figure out how to map your computation onto this massive number of threads. And that is different than the model that we think of. I mean, it's sort of, and it's one of the things that I worry about even in like in OpenMP on multi-core systems. If you sort of think of, I've got a serial computation, I just incrementally try to add parallelism to individual loops, that you don't get, it doesn't help you think about kind of fundamentally from parallelism from the get-go. And so I think that there may be some advantages there. We really should take our codes and try to run them on Fugaku. It's something we've talked about doing, but haven't yet not managed to do that. But I'll certainly reach out to Satoshi and talk about that, because I would like to do a head-to-head comparison on how they perform. Although the question of how much work we put into optimizing for their SIMD sorts of extensions will be really critical to performance. And we're using, for things like k-mer counting, this idea of, each thread is just counting its own sequence of k-mers, which is probably different than the way we would think about it on a SIMD machine, or, with the SIMD extensions. Specialization, I think we are going to see it, and I don't know that it's going to affect the top 500. I mean, I think we may need to think about, we should think about. I actually like the top 500 list. I think it's been really helpful for looking at the history of these machines and how they've evolved over time. But it is very narrow. I mean, it is very narrowly focused on LU factorization for an enormous dense matrix, which is not typically what we do even in scientific simulations. And so I think that we probably do need to look at a broader set of application benchmarks. And I think we may end up with systems that are optimized for different sorts of scenarios. On the other hand, I mean, what's always been the case is that kind of the largest system, is assuming it's not really unbalanced in some way, tends to be something that you can run well on many different applications. And I think that will continue to be the case. But things that, for example, have TPUs or something else for deep learning, and I guess the question is, can they take advantage of narrow data types and as effectively as a specialized architecture? And so I think, and it may still be that in HPC facilities, it makes sense to have more generic sorts of systems, but we are certainly looking at specialized accelerators throughout the high performance facilities. And that will kind of challenge the LINPACK benchmark, I would say.
Okay, thank you very much, Dr. Jelly. we are running out of time, so we will have to stop here. But really, we want to thank you because this was a great talk and we learned a lot in just in less than an hour. So thank you very much. And please, I hope we will keep in contact with you because we have a lot of things that we can learn and hopefully collaborate with you in our work. Thank you very much. And thank you, everyone. So I let the presenter to continue with the next talk. Thank you very much.
Excellent talk by Professor Jelic. Thank you for your presence, and we invite you to continue with your connection. You can also follow us, the event, live on the webpage carla2021.org or on our YouTube channel. We now carry on with our next keynote speaker, Dr. Walfredo Cirne, with the talk, Flex Automatic Quota Management. To introduce our next keynote speaker, I'll now give the floor to Carlos Jaime Barrios.
Hello, everybody. So for me, it's a pleasure and an honor to introduce Dr. Walfredo Cirne. Dr. Walfredo Cirne has worked on the many aspects of parallel scheduling and cluster management for more than 25 years. He is currently one of the researchers that works in the technical institute group at Google, where he leads Flex. This is the subject that we are the pleasure to hear today. Google solution for resource management of the internal cloud. Previously, he was faculty of the Universidad Federal de Campina Grande in Brazil, where he led the Oral Grid project with Francisco Brasileiro. Also, Dr. Cirne holds his PhD in computer science from the University of California, San Diego, and the Bachelor Engineering and Master Studies from the Universidad Federal de Campina Grande do Sul. Thank you very much to accept our invitation, Walfredo, and the public is yours. Thank you very much.
Muchas gracias, Carlos. Hi, everybody. Buenos dias or buenas noches. It's great to be here. Great to see some familiar faces. Today, I'll be talking about Flex, which is essentially how we run the Google internal cloud, right? Google, of course, I'm sure you guys are aware, also has an external cloud that you can go and essentially buy resources, buy access to compute resources. This is built on top of our internal cloud, and internally, the Google applications, not all of them, some of the applications use the external cloud, they're built on the external cloud, but many of them, I think most of them still use the internal cloud, right? This is where we run Gmail and search and everything that Google has in the back end. So what we are going to be talking today is about shared cells. This is a picture of our data center in Iowa. And basically, the way to think about cells, the way we think about cells is a software construct, is an abstract construct that we put on top of our data center. The data center is the hardware construct, is, you know, you guys are all familiar, right? It's a very big cluster. And on top of it, we put a set of services that are running that create a higher level abstraction for the internal developers to run. We call them cells. And in particular, most of our cells, not all, but most of them are shared among the users. And this is really the topic here. So in our shared cells, the basic resources, we call them foundational resources, describe essentially compute and storage. So we have like CPUs, we have RAM describing, and now more and more, we have different kinds of accelerators like TPUs and GPUs and even more specialized accelerators. They describe the compute part. And we have essentially capacity and I/O to describe the storage part, right? So the shells are shared. By shared, I mean that they are much more shared than a typical space-shared supercomputer, right? Every node, every computer in the cell is running hundreds of processes, right? And we run in the cell basically what we call the foundational services, which are sort of the building block for everything. They are brought up to a first approximation without the infrastructure of the cell. They are what makes the cell possible. And there are two foundational services. There is Borg, which is our compute service, right? Essentially, it's a job scheduler, a resource manager. I'm sure that a large part of the audience has been working on that area. It's a little bit tweaked to production load, and I'll go more in detail on that. Then we have Colossus, which is our distributed storage, right? Colossus essentially create a distributed file system. So you can write bytes on a file and not worry about fault tolerance. Colossus will replicate stuff for you and so on. So on top of Borg and Colossus, we run the user jobs, right? The user load. You can write software and then you can submit to Borg and you can start writing in the file system. But also we run what we call composite services, which are internal services that are also available to the internal users. Many of them are also available in the external cloud that help you, just give you a better service than Borg and Colossus, than a simple job scheduler and file system. For example, we have multiple versions of databases, Spanner, Bigtable. We have other services that you do key value store, and services that are specialized for Google, like identity management when you go in Gmail and log in. Those are composite services in our data center that are available to everybody. Now, all kinds of jobs are running in a shared cell. There is very small jobs that have, one task. There is only one process running. There are highly massively parallel jobs with, tens of thousands of tests running, and they all mix together. They have jobs that are serving load, like when you go to Gmail or Google Meet or wherever you are using Google, you are, the back end is one of those jobs running on a shared cell most often. And there is, batch jobs that are doing background process, bookkeeping and doing indexing, doing tests and doing research. So this all mixed together. And there is many users, right? We have this concept very common in the industry of a production user or user group, right? Which is unlike an individual user. Like I have Alfredo at Google. This is my individual account. It's personal. We have these production users that will run on behalf of like a team. And we have a large number of them, over 100,000. So they all mix together and they share the resources. Of course, the reason to share the resources is both efficiency, because we can pack more things together and therefore need to buy less hardware, but also convenience, right? You don't have to be managing machines when you run in the internal cloud, right? You have a much higher level of abstraction. It's just easier to develop and run and do stuff. And users, there is an interesting thing that I think it's more common, it's more prevalent in industry than in academia, like in a large supercomputer center, is that we define obtainability SLO, right? The idea is that you have availability that I'm sure everybody's familiar with, which is you are running, what's the availability you get? How many nines does the platform guarantee you that you are going to have? Because it's not 100%. I mean, at the very least, hardware breaks, right? But availability is very common. Obtainability, we define in a slightly different way. We define it as if you need to run, you are not running yet, right? If you need to run, are the resources going to be available to you, or are you going to go in a queue waiting for resources for your job to start. And obtainability is very strong, is very important, because we want to be in a situation that, for example, we lose a cell, we lose a data center, and we are guaranteed to have resources elsewhere in Google to keep running, right? Such that we don't drop the ball for our users, right? And this is, to a great extent, what Flex is all about. So the problem that we solve is that we provide a guarantee on obtainability of resources that is efficient and does not cost too much toil, right? The way that we have, like, there is this kind of trilemma in resource management for a company, which is, you want to be low toil, you want to have the users doing whatever they want to do. Like if you are search, you want for people to be worrying about search. If you are doing machine translation, people should be looking at translation. You don't want them to be spending time, wasting time in trying to find out resources. So you need low toil. You need high efficiency, because computers cost a lot of money and consume a lot of energy and all of that. So we want to reduce our footprint. And you want to get a high obtainability. You want to give guarantees to people. Solving two of those is very easy. Combining the three of them is tricky. So basically the problem we try to solve is the fundamental problem is to avoid like a tragedy of the commons. If you have a system, and this is very intuitive, but also very true. We tried that in the beginning of Google, right? If you have a system that the data center is there and it's free for all, first come, first serve, you are going to run out of resources, no matter how much you build. Because people are very, very creative in writing loops and consuming a wazoo amount of CPU, right? So what happens here is that if you just do a free for all, someone is going to submit a job that even sometimes has a bug, right? Even it's not intended many times. They do something and this software just run wild and consume like all CPU in the cluster, in the cell. So we had a solution for that, which was in the very beginning of Google, this is how things work. As soon as we reached, a minimal size, this is starting to break. And then we introduced the notion of quota. The notion of quota is a guarantee I give to you that you can consume a certain amount of resources. It's kind of a currency, but it's because the thing who is money is that you may have money, but there is no supplier for you to buy stuff. Like during last year, I'm sure everybody at some point went to the supermarket and had a hard time finding, paper towel, or at least that was the experience here in the United States. But like you may have money, but there may not exist stuff supply for you to buy. The quota is different. The quota is really, you get the resources and they will be there and they will be sitting idle for you to show up. So that's actually a great way to give people excellent obtainability, right? The obtainability becomes equal to the availability of the hardware. It is there waiting for you. Now, it solves that problem I said by solving two aspects, right? Actually by solving one, because the way we implemented quota in the past was that it was manually assigned. So it was, the obtainability was awesome, but it was really, really inefficient. And it was also a pain in the butt because obtaining it, like talking to the humans to solve problems at scale. Remember that Google has like 100,000 or more production groups, was extremely painful. So that's the basic concept that we use until today. But and just to give a little bit of detail on the problems with quota. The problem is essentially that you have all incentives to overestimate your quota, right? You need to do, first of all, figuring out how much resources you need to be running your software. You need to run a benchmark. no one can look at the code and figure out, oh, I need that much RAM or that much CPU, or I need to store that much bytes, or the accelerators or the spindles, the IO I need to storage. You need to measure. So it's actually very heavyweight, and you have all incentives to prepare yourself to make sure that you have resources in the worst case, right? Like you need to put like your resource consumption for fails, right? Like you lose a cell, you better have quota somewhere else to restart your job and keep serving from there. You have like load spikes, so you need to provision for the peak, because fundamentally quota is the resources are assigned to you where you are using or not, right? So it was a very heavyweight process that was very inefficient. The only good thing about it is that it provided a great obtainability. The resources were there waiting for you. Now, Flex is about to make that automated, right? What we want to do is to retain the concept of quota, such that we can actually have as building block our way to provide a strong guarantee on obtainability to our clients. Our clients, again, are the people running in the Google internal cloud, right? And try to be efficient and reduce toil, right? We want a better balance between those three aspects of the problem. Now, the way we do that is that we automatically allocate quota. Instead of having a human allocate quota to you and you have to have a negotiation and explain what you are doing, and this is like this very painful process. Flex is essentially an automaton to allocate quota in demand. So the concept of quota still exists, but we're allocating quota on demand. Now you should be asking, you should very naturally be asking yourself, well, if that's the case, if I just allocate quota to whoever needs, doesn't that just become the free-for-all that I was describing? It's a problem? Because like if people can grab quota, they just submit a job and keep grabbing quota. So the point of Flex is that the automation is smart enough to prevent that to happen, right? Now, we recognize that we cannot make it perfect. We cannot make it such that you allocate quota on demand and people have a value that they can always, in all circumstances, rely on. Because I mean, those two things, to be efficient, we need to have enough capacity for all users and sort of do an on-demand allocation. At some point, this is going to break. We manage the fleet, we manage the internal cloud for that to be rare, but it has to happen when you try to share the resources, that the obtainability you promise is not as good as I have those things that are, I have that amount of resources that is allocated to you and no one ever is going to touch. At the moment someone ever can touch that, you may not get the perfect obtainability. So a very important thing in Flex is how we fail, how we degrade when there are not enough resources. And the policy is that we try to keep whoever is running. The new people coming to the system are the one who will not get resources, are the one who suffer. And this is designed well, for a reason is that it's much better for us to delay the launch of a new product because we didn't plan well and we need, another month to buy more computers and install them in some cell in the world. This is much better as a user experience to our final users. Then, bring down something that's running. The other one is that, this one is a little bit more deep, is that humans really think about production as what is working yesterday keeps working today. When you have a production system that it breaks, the first thing you ask is what changed? What changed to create that, right? So this is basically how Flex works. We still have the concept of quota, we decided to call it as commitment just to disambiguate from the previous system. Google Flex is sort of the third generation of resource management for the internal cloud. The first one was just a free-for-all that I described, and it didn't live so long. Then we created quota, meaning what I just described, the pre-allocation of resources. Then we created Flex. So Flex builds on top of quota. We just call it commitments to disambiguate to the second generation system. Now, there is a ceiling, which a ceiling is an administrative construct that enables the admin to say, yes, Flex is going to allocate resources dynamically to you, but there is a maximum. There is a point that we don't think, and the maximum can be generous, right? This is there to almost to be like a circuit breaker. If your resource consumption runs wild, we are going to catch you before you consume the entire data center. And there is also a floor, which is you may be running something super critical. A good example of that is monitoring, right? Our monitoring stack runs on statically committed resources. So they have a really hard quota that does not reduce, because if the whole cell goes bad, we want at least to have the monitoring to figure out what's going on, right? So the idea is that we are going to give you quota on demand. Whenever you try to run a job, if you are below ceiling and there is enough resources in the cell, we give it to you, and we keep them allocated to you after you stopped using for a little bit of time. Originally, this was 4 days, because the idea would be someone could bring their job down for maintenance, say on Friday, and send the load to some other data center. And then go on the weekend, and they would come back on Monday and have guaranteed that the resources were allocated to them. But that changed a little bit. People argue that they don't do that over the weekends, and now we have a little bit more tight, and actually varies from pool to pool. Because Flex, one concept that's basic to Flex is that we are going to group together to isolate resources on pools, and the pools serve a certain amount of users. So instead of, it's a little bit like the quota world, but instead of giving resources per user, we separate the resources, we partition the resources per pool, and who is in a pool, all the users can, access and have this just-in-time, on-demand resource allocation to them. So how does it work like with a service like Borg? But this is an example who is Borg. This should be more general, because Flex works with Borg, Colossus, and Spanner, and all the services of the internal cloud. But basically, that's a good way to see it is, you are a user, you submit a job to Borg, you talk to the Borg master. During admission control, that talks to Flex to essentially say, does this user has enough resources to run, or should I reject the job? Is this under quota? So the way Flex does is that we look at your commitment. If you have enough commitments to run this job, then done, there is nothing to do. If you don't have enough commitments, we look at your ceiling, and we look at the capacity available in the pool. If you are below your ceiling and there is enough capacity, we automatically give commitment to you on the fly, and whatever is the result, we tell the Borg master, yes, please go ahead and schedule this job, or no, this guy actually does not have enough commitments, there is enough quota, you cannot start this job. Right? Now, all of that essentially enables us to make promises to the users, make promises on the obtainability of resources without having to pre-allocate the resources to them, right? This is something that's very common practice in many industries. Like when you buy an air ticket, you actually do not have the seat in the airplane. usually the companies sell a little bit more seats, a little bit more tickets than seats they have in the plane. And I'm sure that many of you have passed to the not so fun experience of, you know, not having a place in the airplane to fly. Now, this works most of the time, does not work always, but it makes for a very good efficiency, and we go after that. So essentially, we have a model on how much ceilings we distribute to people. The ceiling becomes a little bit like the air ticket, whereas the commitment is the actually boarding pass. You actually have a seat in that plane, right? Because even if we do all the work to figure out precisely how much every user needs, if you do all the benchmark and you compute all the resources you need for fault tolerance and all of that, when you add them up to all the users, right, you get a much bigger value, you get much more resources that if you do the same process to all users together. As a nice side effect of doing that is that you do not need anymore such a precise, well-refined forecast of what each user needs, right? You can, like statistics, the law of large numbers plays in your favor, right? So Flex is all about that, is to give commitments on demand, to give quota on demand. And a key part of it is that the system works most of the time. Most of the time you go to board your airplane with your ticket, and actually they have a seat to you. But a very important piece as well is when the system fails, when we cannot find resources to you, we have a clear policy that the people to suffer are the newcomers, right? This is very important for it to work, because for a company, I think even for general people, like statistical SLOs, like I'm working 99% of the time, they sound great unless you are in the 1% that fail, right? So we need to have a very clear way to degrade gracefully. Now, we make it much better in the point of view of toil. We make it much better in the efficiency, but now we don't have the perfect obtainability that we had with just plain quota, right? Many things can go wrong. There is an inherent trade-off, very fundamentally. The more efficient you want to be, the more likely that you have a stock out. A stock out is your pool is out of resources. You will still have the ceiling, right? You were expecting to get the resources, but the pool does not have resources because we allocated to other people who came before you. We need to fail gracefully and so on, and you want to minimize, but that's going to happen. So we can have like a black swan event. You can have, we call the bank breaker the largest user in a cell. The largest users is particularly tricky because sort of it of course the law of large numbers still works, but the statistical dealing with capacity works much better when you have a very large number of small users, such that each of them can only do a small thing individually. If one of your users is very large, for example, has access to half of the resources in the cluster, they can very quickly bring up a job to consume all of that and make it much harder your risk management. So I just want to give you a few ideas on the risk policies that we have to manage that, because this needs to be actively managed. This is not something that you can do, you know, ad hoc, that you say, oh, this is looking good, I'm just going to give ceilings and Flex is going to take care of that. No, if you do not manage Flex properly, the situation that you get is either that you are going to be very inefficient because you provision much more resources than what you actually need for, say, 99% obtainability, or you are going to be stock out too often. You are going to run out of resources too often, and this is not acceptable to our users. So we need to manage that. I want to give a rough idea on how we do that. Basically, we need a model. We need a model that says, well, given the way the resources in the pool together are being committed, they've been allocated, there is a natural growth. There is a natural organic growth because, you know, people send more emails every day and they take more pictures and you know, like that seems to be the dynamics of computer systems today, is that the demand for compute resources keep growing and growing and growing. When you look them at in aggregate, right, they are relatively smooth and easy to predict, which is one of the great advantages of looking them in aggregate instead of looking to every user individually. So you do a forecast, right? You sort of figure out how things are growing. You put a variance because, of course, this is a stochastic process, and you add a buffer just to be in the safe side, right? Usually what you try to do is that you try to predict far enough in the future to be able to, the horizon you predict really has to do with your ability to buy new computers, install in the data center and have them run. If you can do that, let's say, pick an arbitrary number. If you can do that in 3 months, you need to forecast 3 months ahead to make sure that in the end of those 3 months, you actually still have enough resources to run everybody, who is a very high probability, let's say 99 or 99.9%. And then you need to model what's happening 3 months from now, because if you need more resources 3 months plus 1 day, you need to put the order, you need to purchase them now, right? So just to give a flavor of what we do, this was one of the first policies. This is no longer in production because we evolved it, but this was one of the first policies. We would reason about a concept called allocation, which is, they are not really allocated to you in the sense of commitments or quota, right? But they are sort of what we bookkeep to you when we are reasoning about the capacity. So we would assume that the largest user, the bank breaker, right, the one who can swing the consumption of resources more drastically in one shot, like submitting a job, has all the ceiling allocated to it. Now we would assume in the other end of the spectrum that the vast majority of small users, because this is also a power law, right? As you would expect, there is a few users in Google that consume most of the resources, and there is like hundreds of thousands of users that consume like 20% of the resources, and each of them is really tiny, right? So for those, you don't care very much, and in fact, you don't set ceiling for them in a principled way. Like, you don't ask them to run a benchmark, and you know, this is too much toil. Those are very small users. They are run by a team of, you know, 3, 4, 5 people. You want them to not worry about resource consumption. So we just set a large ceiling for them. We do like in bulk. We do for multiple users at the same time. But for them in our risk model, we don't look at the ceilings. We just assume they are going to grow 20% over the next like provisioning cycle, the time we have to buy more machines. And in the middle, there is the medium users that they are not the bank breaker, but they are large enough for us to be careful on the ceiling we give to them, for us to ask them to run a benchmark and it gives us a prediction. So we assume they can consume 70% of the difference between ceiling and commitments, the part that they can grow into, right? So this was like, gives you a flavor. We are not using this model anymore, but it was the first model and the simplest model, right? That we started with. Gives us a flavor that we need to have an estimate for how much resources are going to be consumed, who is in the replenish cycle, who is in the time we have to buy more machines. more generally, this method can be thought of SLO driven, right? We can have more sophisticated methods, which essentially try to solve the following problem. If you give people expectations, the expectation for the large and medium users is that they actually, we ask them, because they are so large, it's so important for Google efficiency, they are also run by large teams. We ask them to give us a forecast. They need that much resources, and if that's too much, they have to do, a business definition. They have to talk with their VPs and explain why they need so much. For the small users, we give them a low-touch experience because it's not worth to ask them to be involved. They are too small and they are too numerous. They are very amendable to do any statistical modeling, right? We just give them a ceiling that is good enough for them. Now, given that you have two groups of users and you want to have a target, you want to say the pool is going to be stocked out, I'll be in the situation that I don't have resources for the next guy, only 1% of the days. So you can sort of create a model, and there is multiple variants on these models. You can use multiple different statistics approaches to do that. You can also use NL as a reference to the previous talk, that we can actually revisit lots of the existing problems that we've been playing with for decades or more with ML. And you need to take in consideration all the obvious signals that you would look. You need to look at the growth. You need to look at the variance in the growth. You need to look at your replenish time, which is how much time you have to, land more compute in your cells and so on. How much risk you want to take, and all of that. And more recently, we started seeing more demand for us to configure Flex to non-production load. This is a direct consequence of the increased power and popularity of AI. Now we have a lot of load that's training load, and people doing experiments and trying to tweak models and things like that. So that actually is a little bit closer to what you get in a supercomputer center, right? That you are not running a production load that has to be up like 24/7 all the time. So it's acceptable in this situation that people queue. And we extended Flex to support weights, a little bit like DRF. Like in contention, you get a chunk of the resources that is proportional to your weight. We did introduce queuing to prevent churn, because if you implement things like proportional share, DRF, and then use weights and so on, if you do that in a granularity, in a time grain that is too small, you end up causing a lot of preemptions and a lot of churn. So we use a generous sort of time horizon to converge that. But again, this is not our serving load, and it's a more recent development in Flex. One important thing, I think I already covered that. I need to reorganize these slides. I already covered that, is that the basic model is that you have commitments which are really like quota, non-oversubscribed quota, right? It is there. And Flex will allocate commitments to you on demand based on the ceiling. We only explicitly set the ceiling for a very tiny part of our users, which are the largest users. They are few, but they consume most resources. So we actually go to them and set the ceiling very consciously. For almost everybody else, we set the ceiling like in a wholesale operation. We just give a default. We were finding that finding a single default for everybody was tricky, so we introduced this concept of circles, which sort of manages people in different categories. So imagine that you are dividing users in small, medium, and large, and we create self-service that a user that is small is growing. It's noticed that it's going to hit the ceiling that sort of is applied to all small users. And then they can go to the system and ask for an upgrade for medium. The system will look if they are being good people, like if they have good utilization and so on, if they should sort of, instead of being asking for more resources, should be fixing an efficiency problem on their own service. And if the risk model tells we can do that, which usually is almost always the case, then we grant them to go to the medium, and we create automation for that to happen. Because it is just not possible to be dealing with hundreds of thousands of users, in this case, production groups, right? Again, this is not my personal user, Alfredo, it's the production group, on a one-on-one basis, right? We need to scale. Oh, this is a very interesting part and actually subject of very active research right now. As I said, you know, Borg and Colossus are the building blocks. They are the foundational services. They give you compute, they give you the ability to run a job, and they give you a distributed file system. But we have multiple things built on top of it. For example, we have Bigtable and Spanner, which are not serving the final user. They are not, you know, like Gmail or Search. They are instead creating a service that's used internally. They are clients of Borg and Colossus. They use Borg to run their jobs, and they use Colossus to store the data. The thing is that we want the size of the Bigtable. Bigtable also has a capacity. It is not a capacity denominated in foundational unities anymore. It's denominated in composite units. It's denominated in Bigtable. But we don't want to leave a fixed amount of Bigtable existing in the cell, because either we are going to err too much or too little. If it's too much, we are inefficient. If it's too little, the users cannot run, which is even worse. So we scale. Flex essentially looks at the Bigtable consumption, how much Bigtable is being consumed right now. And we convert that to Borg and Colossus, right? We have a translation function, which is a certain amount of Bigtable to be provided requires that much Borg and that much Colossus. So we keep track, we have a control loop. We keep track of how much Bigtable is being used now. And if users of Bigtable are close to exhaust the Bigtable capacity, we scale Bigtable up. We make more Bigtable available. On the other hand, if the usage goes low, very low, and there is just a lot of Bigtable allocated and not being used, we will decrease Bigtable or any other composite service. This works really well. Unfortunately, this is based on an approximation that's very coarse, and it's becoming worse and worse as hardware becomes more heterogeneous. The approximation is that we have this notion of translation function. This XFN here is translation function, is the actual amount of Borg and Colossus you need actually vary with the load. Like imagine a database, right? How much QPS the database can support. That is really like a Bigtable unit. That's the Bigtable capacity should be talking about QPS and should be talking about how much data you are able to store in the database. So the problem is that how much transactions you can support do depend on the transaction. They are not fixed amount. Even though our infrastructure assumes they are fixed amount, this is actually a very active area of research internally, how we can do better than that. And of course, I mean, we can create translation functions that are richer, but it's tricky. It has side effects when we do that, because essentially when we recognize that the capacity depends on the load, it's what would be a good analogy? Let's say that you have a bus. The bus then has 40 seats, and everybody would expect that if you have 15 people boarding the bus, now you have 25 seats available, right? This is how everybody thinks about capacity. Capacity is like Newtonian. It's additive, right? You have 40, you use 15, now you have 25 available. But what happens is that maybe those 15s, they have, you know, like one mother and a baby, and the baby is going to be in her lap. And actually you only took 14 seats. Because of the 15 people that boarded, the mother and the baby are using only one seat. Now capacity is no longer additive, as you would expect. You have 40 seats, 15 people boarded, and you have like 26 available, right? Not 25. And this is kind of the challenge that we have to deal with that. This is very active area of internal research for us. And yes, I mean, this came, last time I gave this talk, people said, this business of quota and commitments that, you know, it's very zero sum and you allocate and you are done. But how do you do oversubscription? Like we had a paper we published in the past that shows that if the SLO is lower, right, we can actually manufacture capacity with a very high confidence. And we do that. The way we reconcile this with this very foundational notion that Flex deals with commitment and they are not oversubscribed is that we create extra capacity at a new tier. So Borg today has like 4 tiers, like a highly available tier, a mostly available tier, weekly available, and a best effort. They're like 4 grades, and they do come with an SLO, and that's really a great, it has enabled us to oversubscribe much more aggressively our fleet with safety, right? Because for a company, we want to oversubscribe to be efficient, but we want to make sure that, you know, our load keeps running, that Google does not go down because we oversubscribe too much. So the best way, or not the best way, a key way that we find to make this happen is to make sure that the resources that we oversubscribe come with a guarantee that's weaker than the prime one, right? This way, we can select load that goes to the oversubscribed resources. For example, if you have a background processing that needs to run every day, and you can be moved to run during the night when there is much less demand on the data centers, because the cells, the data center have a diurnal cycle, you know, that varies every day very consistently. You need a guarantee. Your job is key to Google. It needs to run every day, but it does not need to consume prime resources. We have about order of 10,000 flex pools in the internal cloud because we have multiple cells, hundreds of them, and because a pool really is for a particular service. We have like Borg pools and Colossus pools and, you know, big tables pools, spanner pools, and so on and so on. It creates a single point for oversubscription and management of resources, which is very nice, and enables automation. So it's a very large scale system that runs and really controls Google's internal cloud. There is, of course, a lot of related work in the area. I want to point out a little bit. External clouds have the notion of quota, but this is much more to prevent fraud, right? They want to prevent the case that someone fakes up an identity or a credit card, show up, does Bitcoin mining for 1 month and disappears without paying the bill, right? So this is very different. The other one is that what we do for, typically we do for high performance computing and you know, how we share resources in contention. There are things like wait and share with DRF that we do implement, but they are used for the piece of our load that can actually tolerate low obtainability. If you are running, you know, we are using Zoom now. I'm sure Zoom would not be happy if they were using a platform that you can submit your job. Sometimes it's going to be queued for hours or even days. That doesn't cut for really production load. Flex today covers most resources in Google. We cover 3/4 of absolutely all resources. And we cover 100% of the active shared resources. Because there are some resources in Google that are not shared. They are dedicated to some particular applications. For example, our network edge that does, DOS prevention and load balancing and so on is all dedicated, and there is good reason for that, right? I mean, it's not shared. And there are gory details on why that's the case. And every now and then we have a breakthrough on some isolation technology that enables us to move more of the load that's dedicated to shared. And there is also resources that are not active, right? That are, in transit or being built and so on. And of course, if they are not active, Flex cannot control them. But for if you come to Google, do an internship or a sabbatical or join to work here, chances that you are going to be touching Flex are extremely high. More than 99% of the internal users do use Flex because the dedicated piece is really small. It's large and important, but really small. We have about 10,000, order of 10,000 pools, as I mentioned. And Flex is very active, like the whole notion of adjusting the commitment, giving you quota in demand, we do that more than 2 million times a year. A day, 2 million times per day. So the summary is that we need quota to do strong obtainability, but we need to automate to reduce toil and to be efficient. Now, when we do that, we need to make sure that we manage the risk of stocking out. And there is no single policy that makes everybody happy. That's one of the reasons that we have multiple pools. Even for the same resource, like Borg, in the same cell, we often have multiple pools because they are managed by different people who is different risk tolerance for that set of users, right? We have been improving on that. And it's a preventive solution at Google. If you come to Google, you are most likely going to use it. And my sales pitch, we are hiring. If you find all this area interesting, please send me an email. We'd love to have you join the fund. And I want to give a little bit of time to questions.
Dr. Wilfredo, thank you very much. A very interesting subject. So now it's time for questions, but in the middle, I have a couple of questions for you. In fact, so the first one is about the use of Flex in production system. So for me, it's curious to see when you propose some management for the risk, there are not a real affectation in the performance. So I don't understand why.
Say again, Carlos. Sorry, I didn't get the question.
Yes, in fact, for the when you propose different politics to risk management, it's not visible affectation in a negative way of the performance. But this is impressive for me. Why they are not?
Why we have different risk management policies, right? That's the question.
Yeah.
It's fundamentally because whenever you pick a risk management policy or model or technique, you are choosing a trade-off between efficiency and obtainability, right? If you want to have obtainability all the time, your efficiency is going to be low because you need to be super conservative. In the extreme, you need to go back to the quota model. Flex, by the way, supports the quota model. It's just you give the floor of commitments to everybody, and then everybody has a commitment and sort of you fall back in the quota model. But you don't need to go to that extreme. You can still have very conservative policies that will run out of resources very rarely. And some of our clients want that. Like the example I gave of the monitoring stack. The monitoring stack runs in a Flex pool that is configured very conservatively, extremely conservatively. And we have like fallback mechanisms and so on that are implemented ad hoc to make sure that monitoring is always running. Because you need monitoring to be always running. Otherwise, when you have a problem and you don't have monitoring, you cannot fix the problem. Now, in the other extreme, is that imagine that you have a bunch of researchers doing AI research and try to calibrate models and so on. For them, efficiency is very important. They would prefer to actually wait. Their need for obtainability is not so, I mean, it's a trade-off. I mean, if you ask them, do you want to wait? They say, of course not. No one wants to wait. You want to submit the job and run now. But they really want the efficiency. They want to use all single resources. So in trade-off, they are actually okay to wait a little bit, and then we sacrifice the obtainability in that pool. That's really the need for different models, because different load will value this trade-off in different ways. Like I think most people working with supercomputer centers, high performance computing, and so on, they are used to maximize only for efficiency and really ignore obtainability, right? I mean, like many supercomputer centers, they give like a budget in CPU hours per year, right? But if everybody tries to use at the same time, because it's the week before a huge conference, the system gets congested and so on. So it's just different points in the trade-off.
Okay, thank you. We have another question in the panel. So it's from Robinson Rivas from Venezuela. So he asks, when you say 75% of the Google resource, which resource are you referring to?
Referring to resources that exist in our data centers.
Okay. So only for the internal servers, I think, no? I mean. And the other question that he say is the problem that happened recently with the Facebook service. Do you think centralizing management is not a risk bet?
Sorry, Carlos, you cut a little bit for me. Could you repeat the
Yes, sorry. So the problem that happened recently with Facebook, do you think centralizing management is not a risky bet?
There is definitely a risk that comes with it. I mean, there is no denying, right? The question is, all this area is about trade-offs, right? I mean, you need to manage the risk that comes with it, because it's really about a trade-off. You are trading off risk versus efficiency, and the extremes are bad, right? Because if you want to isolate absolutely everything, then maybe Facebook and WhatsApp and Instagram don't go down at the same time, but it's going to be more and more expensive for Facebook to run that. Now, you try to get a sweet spot where you get the best of efficiency and sacrifice the risk the minimum amount possible, right? I try to cover that trade-off here in the talk, talking about resources versus stock out, obtainability versus stock out. The problem with Facebook was, as far as I understand, I mean, don't work for Facebook, but what's out there on is that people pushed a configuration to their DNS and BGP that was wrong, and that's what brought Facebook down, right? Now, there are ways to address that that are compatible with Flex and the techniques I've been talking to. Is that you try not to have like global configs or global anything or single points of failure, which you can do in a system like that, right? So it's about managing the balance.
Okay, thank you very much. So we are in time. Thank you very much, Wilfredo. So for us, it's a pleasure that you have here with us. I hope that the next time, maybe in real, I don't know, be here in Colombia or in Brazil. I don't know. So
yeah,
or in Silicon Valley, I don't know.
glad to go and hopefully see you guys in person. I have to tell that the talk is much more fun when I can see people's face. Talking to the computer screen without feedback is tricky.
Yeah.
But I hope it was good enough and that you guys enjoyed.
Yeah. Ok, muito obrigado. Thank you.
Nada. Good
Okay.
to see you guys.
Okay.
See you, Navo.
Abraços. Obrigado, Alfredo. Tchau, tchau.
Meu prazer. Tchau, tchau.
Tchau.
Okay, so now we invite to all the participants to the room for the track HPC and AI in the session 1. In the other room, the address for the room and the link, sorry, is in the chat of this session. So see you in the other room. Thank you.
Recording stopped.